Welcome to the Linux debugging course. Linux is the most widely used open source operating system, powering countless devices and systems worldwide. Debugging plays a crucial role in ensuring the reliability and performance of Linux-based systems. This course offers a structured journey through debugging techniques in Linux, covering the entire stack from user space to kernel space. In this course, you'll learn about the various Linux debugging tools and methodologies through demonstrations and examples. By following and understanding the material provided, you will gain many practical insights into this knowledge domain. For Linux developers and system administrators, understanding debugging techniques is essential for identifying and resolving issues effectively. While the information on Linux debugging tools and methodologies is often scattered across the internet, this course is our effort to consolidate and present it as a single comprehensive guide.
Hi, my name is John O'Sullivan and I am a software architect with over 30 years of experience in Linux embedded systems. I have extensive hands-on expertise in hardware-software integration and product development in a wide range of industries. One of the difficulties in learning Linux is the need to sift through the vast amount of information that's out there. Linux changes year to year, and much of the material that's there could be obsolete or no longer relevant. That's why in this course we have gathered together what we feel are the essential tools, techniques, and information that is required to be successful in this particular knowledge domain. We enjoyed putting together this course and we hope you enjoy this course as well.
Hi, my name is Manas Marwa and I'm a principal embedded engineer with over 13 years of experience in embedded Linux. I specialize in product development using embedded Linux across various domains including audio, video, and networking. Through this course, we aim to equip you with the knowledge and skill set required to tackle the complex and real-world debugging challenges across the Linux operating system. We welcome you all to the course.
This course is organized into multiple modules, and each module is designed to cover debugging techniques across the entire stack from user space to kernel space in a structured and systematic manner. We will start with the Linux OS system itself, discussing the fundamental architecture and structure of the Linux operating system. In the second module of this course, we will explore the basic Linux analysis and observability tools available to us. These foundational tools serve as the first level of debugging and are helpful in providing insights into the system's state and behavior. The third module of this course looks at how we can dissect application binaries with tools like binutils and how we can employ powerful debugging applications like GDB for more in-depth analysis. The fourth module is dedicated to addressing common memory issues in user space applications, along with exploring related tools such as Valgrind and sanitizers, which are designed to detect and resolve these issues before the code is deployed. Module 5 focuses on tracing in Linux. Tracing is an essential technique for monitoring and recording software behavior and execution flow at runtime. This module explores a variety of tracing tools to analyze both user space and kernel activities. Module 6 dives into profiling in Linux, emphasizing the collection and analysis of data to identify bottlenecks in performance. We'll explore memory-based and execution-based profiling and use data visualization techniques like flame graph to interpret and understand the data. The final module, Module 7, is dedicated to kernel debugging techniques. It covers essential debugging directives such as logging and dynamic debugging, along with a deep dive into kernel OOPS analysis and the various kernel-level sanitizers at our disposal. Additionally, we'll explore the kernel debugger, KGDB, and learn how to debug the Linux kernel using this tool. Please note, modules 5, 6 and 7 will be covered in the second part of this course. Before we dive into the course, I'd like to highlight important information about the course. The course materials, including slides and examples, are hosted on a GitHub repository for easy access and reference. In the course videos, we will provide explanations along with demonstrations of the course examples. For simplicity, all demonstrations are based on Ubuntu 22.04, and we recommend that you try out the demonstrations yourself as the course progresses to gain hands-on experience. Please review the instructions for building the course examples before proceeding. We value your feedback and suggestions, so please share them via email at specialistlinuxtraining@gmail.com. For corrections on the training material, please feel free to raise issues and pull requests in the GitHub repository. Thank you for choosing this course, and we would now like to welcome you to the Linux Debugging course. Welcome to part 1 of the Linux Debugging course. This section will take a look at the architecture of the Linux operating system, allowing you to understand the differences between terms like Userspace and Kernel space. We will also examine the different modes of execution, introducing the concept of privilege and access, and then finally we will look at how these distinct spaces provide mechanisms for exchanging information. It is important to understand these building blocks before moving on to the Linux debugging tools and techniques, which we'll cover later in the course. In this section, we will look at the Linux operating system architecture. The Linux operating system architecture is divided into two main parts, a user space component and a kernel space component. These are shown on the diagram on the right-hand side. User space is a protected virtual address space that hosts user applications like web browsers, word processors, games, media players, and Office applications. It also hosts system libraries, and these are normally shared libraries that provide common functionality to multiple user applications. Additionally, it provides user-level services, and these can be things like web servers like Apache, database servers like MySQL, and application servers. Kernel space is a privilege mode reserved for kernel functionalities. And these would include device drivers, interrupt handlers, which respond to hardware interrupts generated by devices like keyboards, mice, and network adapters. It also hosts the process scheduler, which is responsible for determining which user-level process gets CPU time. And it also provides memory management for managing the physical and virtual memory. We spoke about the essential difference between protected mode and privilege mode, and this difference is critical in understanding what can be done in user space versus kernel space. Because the kernel mode is allowed to run all privilege operations, it provides most of the key services that allow user space programs run, like scheduling and memory management. And it also deals directly with hardware, handling interrupts and moving data to and from that hardware. Because a user mode application is only allowed a basic set of operations, it must request certain privileged services through the kernel, and it does this by using system calls. These system calls facilitate activities like reading and writing to disk and transferring data from the network via sockets. We will look at these system calls in more detail in a later slide. This slide shows the address space for a 32-bit system. The top 1 gigabyte of memory, labeled kernel space, is reserved for the kernel, and this is divided into low mem and high mem. Low mem is used for various system resources and critical kernel data structures. High mem is the portion of memory above the 896 megabyte boundary on 32-bit systems. This distinction was historically significant for managing memory on 32-bit systems, which had limited addressable memory, but is less of a concern now on modern 64-bit systems, and we'll see this in subsequent slides. The lower portion of the diagram shows the 3 GB space that is reserved for Userspace. We will look at the random offsets and the organization of this memory in more detail in the slides that follow. In the previous slide, we saw that each process has access to 3 GB of a virtual address space on 32-bit systems. The structure and organization of this space is managed by a process descriptor called task_struct. The page tables and memory mappings for a process are defined in mm_struct, and we will look at this in more detail in the next slide. You will also have noticed in the previous slide that the offsets to user mappings are randomized. This randomization minimizes the possibility of an attacker being able to predict the location of data structures associated with a process. This randomization can often make debugging a little more difficult, so we can disable it by setting the no rand maps command line option to the kernel, or by echoing 0 to proc sys kernel randomize VA space. Task_struct represents the overall state of a process, while mm_struct is responsible for managing the process's memory, including its virtual address space. This relationship is shown in the diagram. The field in task_struct connects the process to its memory management structures. mm_struct contains important information about the process's virtual memory layout, such as the start and end addresses of the various sections of memory, page tables, and more. We can view the mappings managed by these structures by examining the map associated with a process in the proc file system, and we will look at this in a little more detail later on. As we saw in the previous slide, VMAs, or virtual memory addresses, are memory zones set up by the kernel when it initializes a process. These memory sections, or zones, are defined by task_struct and by the memory management structure mm_struct. The different zones can have different read, write, and executable attributes. A segmentation fault can occur when a program attempts to access a non-existent region, or when it tries to perform an operation on a section of memory which does not permit that operation. A common example of this would be when it tries to execute data in a non-executable segment, or when it attempts to write to a read-only segment of memory. The per application maps are located in the proc file system, and we can locate these by examining the data at proc process ID maps. In a later section of the course, we will provide a more detailed examination of the information that the kernel exposes through the proc file system. Kernel logical addressing. We saw in a previous slide that KLA, or kernel logical addressing, sits above Userspace and is mapped directly to low memory in physical memory on 32-bit systems. The config_page_offset defines the logical address space at a fixed offset relative to physical memory. The kernel provides the macros shown to make the process of translating between physical and logical addresses easier. The kernel logical address range is in physically contiguous memory, and this guarantees that there is no fragmentation, and so the memory is suitable for allocating per process stack space, memory for DMA, and memory requested through the kmalloc call. Kernel virtual address. Kernel virtual addresses, also called HIMEM because they map to memory beyond the 896 megabyte boundary, reside at the top of the kernel address space. High memory on 32-bit systems is a region of physical memory that is not directly mapped but is instead accessed through various mechanisms such as paging or memory mapped I/O. Because we do not require the data to be physically contiguous, these virtual addresses are suitable for large buffer allocation in the kernel. For example, memory mapped IO, insmod, IO remap, kmap, or vmalloc. The MMU and TLB, which we will look at in later slides, can manage the fragmentation of data in physical memory so that we are provided with what appears to be a virtually contiguous address space. Because kernel virtual addresses are not physically contiguous, this makes them unsuitable for some operations like DMA. We now turn our attention to the 64-bit address space. Because of the large address bus, we can now access a much larger space. Many of the concepts like high memory and low memory are no longer relevant here because a much larger address space gives us the flexibility to map memory as we wish. It should be noted that not all 64 bits are used for addressing. Using all 64 bits would provide an address range far greater than we would ever need. So the x86 64-bit architecture, for example, only uses 48 bits for addressing. Other architectures have variations on this. On 64-bit systems, we have the concept of a user space virtual address and a kernel space virtual address. Virtual addresses are stored as 64-bit values, with the least significant 48 bits used as the main address, and the most significant 16 bits used as an indicator of which address space you're in. For kernel virtual addresses, the top 16 bits are always set to ones, and for user space virtual addresses, the top 16 bits are always set to 0. Looking at the address space diagram and reading from top to bottom, we can see that the kernel address space is 128 terabytes. This is often referred to as the canonical higher half. We then have a whole or region of non-canonical addresses that are unused, and then we have the user space virtual address range, also referred to as the canonical lower half, which is also 128 terabytes. This diagram is typically for the x86 64-bit architecture, but remember, other 64-bit architectures use different numbers of address bits and different splits for the kernel and user space. As we saw in the previous slide, on a 64-bit system, each process has access to 128 terabytes of virtual address space. The basic layout of memory sections in the user space virtual address map, such as heap, stack, text, data, shared libraries, are much the same as in a 32-bit system. The primary difference in user space layout between 32-bit and 64-bit addressing spaces is the significantly larger addressable range in the 64-bit architectures. As we noted, not all 64 bits are actually used for addressing. This larger space provides more flexibility for memory allocation, mapping, and shared libraries, and it also allows for more efficient memory management and utilization in modern systems. We do not have the constraints of high and low memory concepts that we experience on 32-bit systems due to the limited addressable range. For x86 64-bit systems, the most popular kernel user space split is at address 8, all zeros, and for ARM64, it's at FFFF88, all zeros. Other architectures may use different schemes. In this slide, we will take a more detailed look at the user virtual address space for 64-bit systems. The first thing to note here is that we see the addresses are using only 48 bits, and this is because in user space, the top 16 most significant bits are set to 0, as we discussed in a previous slide. The layout shows the start and end addresses of each section and the associated permissions for that section. We can see the familiar sections for executable code, for the heap and the stack, and in the shared library section, we see a region that's used to map various shared libraries. In this instance, we see a mapping to the C library, which is an essential system library that provides fundamental functions and services to user-level programs. We also see a mapping to the linker loader for 64-bit executables, and it's responsible for loading shared libraries and resolving symbols at runtime for dynamically linked programs on a 64-bit Linux system. The virtual dynamic shared object area has two sections. There is the vvar memory range, which is a read-only area that allows Userspace programs to more efficiently access certain kernel-related variables and data structures. And this is particularly useful for time-related operations. The VDSO memory range is a region that allows Userspace programs to efficiently access certain kernel functions without making full system calls. This region is readable and executable, but not writable, meaning the Userspace programs can read and execute code from it, but cannot write to it. We can now look at the 64-bit kernel virtual address space. As can be seen with the addresses on the left-hand side, we are in kernel space because the most significant 16 bits are all set to 1. The kernel address space on the 64-bit systems is more complicated than the 32-bit equivalent. In this map, we can see a number of areas, which we will cover in detail in the next slide, that are dedicated to various types of memory allocation. We can also see an area labeled Kasan shadow memory. Kasan is the kernel address sanitizer, and it is a dynamic memory error detector tool used in the Linux kernel to detect various types of memory-related bugs, such as buffer overflow, use after free errors, and other memory access issues. Kasan works by instrumenting memory allocations and deallocations, and uses this shadow memory to keep track of memory metadata and detect memory errors. It is a powerful feature for debugging memory-related problems on modern systems. We're now going to look in a little more detail at the 64-bit kernel address space that we saw in the previous slide. The direct mapping of all physical memory, page offset base, is a region in kernel space where the entire physical memory is directly mapped for efficient access. This area allows the kernel to access physical addresses efficiently without needing complex translation. It's often referred to as a linear mapping because the virtual address for each physical address is simply an offset. It provides the kernel with a straightforward way to interact with physical memory, which is necessary for the low-level operations that include managing page tables, handling interrupts, and performing device I/O. The vmalloc I/O remap space deals with two types of allocation. The vmalloc region is managed by the kernel's virtual memory manager and provides a way to allocate and access virtual memory regions that may not be physically contiguous. It is used for storing data structures that don't need physical memory continuity. The I/O remap space is used to directly map physically non-contiguous I/O regions that need to interact with hardware devices. The kernel uses the virtual memory map VME mmap_base to access and manage physical memory pages, including page tables and other data structures required for virtual to physical address translation and memory allocation. And the CPU entry area mapping allows the kernel to maintain separate data structures and state for each CPU. This is critical for efficient multi-core and multi-processor system management. The extended stack pointer fix-up stacks are used to handle exceptions during context switches and when the kernel starts execution. These stacks are used to ensure proper handling of CPU state during such operations. Kernel text mapping, which is mapped to physical address 0, is a region in the virtual address space of the Linux kernel that contains the actual executable code of the kernel itself. It is mapped to a fixed physical address, typically at address 0 in physical memory. This read-only fixed mapping is essential for the bootloader and hardware initialization routines to locate and start executing the kernel code. Module mapping space is a region reserved for dynamically loaded kernel modules, allowing the kernel to load and manage modules separately from its main code. And this is an essential feature of modern kernel development. Kernel internal fixed map range, variable size and offset is a region with variable size and offset used for mapping kernel internal data structures and hardware register addresses, and it ensures efficient access to this type of memory. It is used typically for memory regions that need a consistent and predictable virtual to physical mapping. The size and offset of this range can actually vary depending on the architecture and the specific configuration of the kernel. In this slide, we summarize the virtual addressing that we've looked at in the previous few slides. So we saw user virtual addresses, and these are addresses used by user-level processes. They are an abstraction that allows each process to have its own dedicated virtual memory space, which is mapped to physical memory by an MMU. We also looked at kernel logical addresses, and we saw that these are a mapping from kernel space virtual addresses to physical addresses. The mapping is in low mem on 32-bit systems, and they use a constant offset that provides a linear one-to-one mapping to a physical address. This memory, allocated with functions like kmalloc, is contiguous and cannot be swapped out. And for this reason, these allocations are suitable for operations like DMA. We also looked at kernel virtual addresses. Kernel virtual addresses map to the high mem part of physical memory, which is the memory beyond 896 megabytes on 32-bit systems. These are not physically contiguous, but they are virtually contiguous, and this memory is typically allocated with vmalloc, and this area is suitable for insmod and similar operations. It should be noted that when dealing with addresses in Linux, we are always dealing with virtual addresses. We are generally not exposed to the physical addresses. In this slide, we're going to look at some of the hardware components that are involved in memory management on a Linux system. The memory controller is responsible for controlling the flow of data between the CPU and the computer's memory subsystem, including the RAM, cache, and other storage devices. The memory controller manages tasks such as reading data from memory, writing data to memory, and coordinating memory access requests from the CPU to other hardware components. The MMU is a hardware component or subsystem within a CPU or processor that is responsible for managing memory access and translation between virtual addresses used by the software and physical addresses in the computer's RAM. The primary function of the MMU includes address translation, which is the converting of virtual addresses to physical addresses, memory protection, and that's preventing unauthorized access to certain memory areas, and managing memory allocation and deallocation. The TLB, which is a translation look-aside buffer, is an additional component that plays a critical role in improving the efficiency of virtual memory systems by accelerating the translation of virtual addresses to physical addresses. This translation process can be slow if performed by the MMU, so the TLB caches frequently use translations to speed up the process. We will now focus on the MMU in a little more detail. A Userspace process runs in a virtual address space, and we've seen this on previous slides. The MMU facilitates the translation from virtual to physical addresses. The base unit of an MMU is something called a page, which is fixed in size, and that size depends on the underlying architecture. On x86 systems, the most commonly used page size is 4 kilobytes. This page size is often referred to as the standard or default page size. It is the smallest unit of memory that the memory management unit can manage. The MMU hardware uses mappings in a page table for address translation. In modern computers, the virtual address space of a process is often much larger than the physical memory available. Creating a single monolithic page table that maps all possible virtual addresses to physical addresses would be impractical due to its sheer size and memory requirements. Multi-level page tables help manage the sparse address space much more efficiently. In a multi-level page table, it is more efficient to have the first and second level page tables in memory, while other levels can reside on the disk. In the next two slides, we will look at page fault handling in Linux. In this diagram, we can see a process that is running and which suddenly encounters a virtual address that is not mapped to physical memory. The operating system raises a page fault and puts the process to sleep. The page fault handler checks the validity of the request. If it is not a valid request, it raises a segmentation fault. Otherwise, it tries to honor the request using the TLB and the page table. In the next slide, we will look at these steps in a little more detail. As we saw in the previous slide, if a user application tries to access a virtual memory address which is not mapped to a physical address, then the MMU triggers a page fault. The kernel, on receiving the page fault interrupt, invokes the page fault handler and performs the following operations. It first suspends the Userspace process, allowing it to sleep. It then finds the mapping for the offending address in the page table. If there is space in the TLB, it can add the new mapping. If not, it must remove an existing entry before copying the required page frame. The page frame may be in RAM or may be in disk. After it has created a TLB entry for the page containing the address, it wakes up the Userspace process, which resumes operation. We can think of the TLB as a cache of sorts that stores frequently used virtual to physical address mappings, and this helps improve memory access times. The degree to which pages are stored on disk depends on the amount of available RAM. When RAM becomes scarce, the OS can move the less frequently used pages from RAM to the page file on disk, freeing up physical memory for other tasks. The worst case impact in terms of performance for a page fault occurs when the page frame has to be fetched from disk. User process mappings, part 1. Each process in user virtual address space has its own mapping, and this mapping is changed during a context switch. The memory map for a user process will have many mappings. Each of these mappings can cover multiple page frames in physical memory. The same virtual address can be mapped to different physical addresses for different processes, and we will look at this in more detail in an upcoming slide. Because the TLB is a limited resource, far more mappings can be made than exist in the TLB at any one time. So the kernel must keep track of all mappings, and it stores this in page tables instruct_mm and vm_area_struct, which we looked at in the earlier slides. A mapping to a virtually contiguous space does not have to be physically contiguous. This is always true for user space processes, and this makes allocation easier because we can provide large, virtually contiguous areas which can map to fragmented areas across physical memory. The TLB and the MMU hide and manage this fragmentation. In this diagram, we look again at the mapping of a user space program to physical memory using the TLB. We can see that process 1 maps to certain virtual addresses, which the TLB then maps to areas in physical memory. When we look at process 2, we can see that it also maps to some of those same virtual addresses, but the TLB can map these to different areas of physical memory. So it is not unusual to see processes using the same virtual addresses, as the TLB will manage the mapping of these to different areas of physical memory. The facility of the TLB to manage different mappings is also used in shared memory. Shared memory in Userspace refers to a technique used in operating systems to allow multiple processes to access a region of memory that is shared between them. And this can be useful for inter-process communication or to share common memory-based resources between different processes. The MMU and TLB maps the same physical frame into two or more processes. And this can be seen in the diagram with the shared area shown in physical memory mapped to different virtual addresses in each of the separate processes. The mmap call allows us to request specific virtual addresses to map a shared region.
We will now turn our attention to the shared memory example. We've provided some sample code for this, a program that writes to shared memory and a program that reads back the written data. In order to successfully read from shared memory using the read example, we first need to execute the write example, and this will initialize the shared memory segment and write data to it. When that is done, we can then run the read example and use the existing shared memory segment to retrieve the data. So looking now at the write example, then we have the definition of the shared memory size. Then we initialize some of the key variables that we will use in this example, including the ID and the location where the data will be written. We then generate a unique key by combining a path with a character identifier, and this combination generates a unique key for the shared memory. We check for any errors associated with that process. And then we create the shared memory segment. And to do this, we call smhget with the key we earlier created, the shared memory segment size, and an indication to create the segment with particular permissions. We again check for errors. We then attach that shared memory to our process. So the shmat command will take the ID and then return an actual address that we can write to. We again check for errors associated with this. We can then write the actual data, and once the data is written, we can detach the shared memory segment from our code. Turning our attention now to the read example, we again set up the same variables. We define the shared memory size. We generate the same key because we are interested in retrieving data from the previously created shared memory segment. We check for errors. We get the shared memory segment using the key. And then having got the shared memory segment, we use the ID of that segment to attach the shared memory to our process. We can then simply read from that segment as we do here in the printf statement. And then finally, to clean up, we again detach ourselves from that shared memory segment. To build this, we use a standard CMake list file. We add an executable for the read and write example, and then link it to the RT library, which provides the shared memory functionality. We use CMake dot to create the make file. We then make the examples. We execute our write example, and then a read example, and we can see that we have retrieved the memory written in the write example as shown here in the output from our read example.
A process is an instance of a running program that has its own memory space, system resources, file descriptors, network sockets, and environment variables. Each process is assigned a unique process ID, which we often refer to as a PID, and information related to a process can be accessed from the proc file system using this PID as a reference. We will use this facility in some of our later examples. The kernel keeps track of all user space processes through a task vector, which is an array of task struct pointers. The current pointer in the kernel points to the currently running process. This can also be accessed through the getCurrent function call. We will now look at a brief example of the getCurrent call in a simple kernel module, and we include this in the examples we provide. In this simple example, we can see the getCurrent call, and this returns a pointer to the current executing task. In this simple program, we periodically print out information about that task, its name, and its associated process number. We build our module and then install it as a kernel module. And now checking the message, we can see that the current process name and PID is printed. And we can confirm this with the ps command. In this instance, we can see we are looking at a kernel thread because of the square brackets around the process name. And we can also see that its PID corresponds with the entry in syslog that we examined with the message. A thread is a lightweight execution unit within a process. In our diagram, the overall structure represents a process, and this particular process has 3 distinct threads. Threads share the same memory space and system resources as their parent process, but they can have their own registers, stack, and program counter. And again, we can observe this in the diagram. Threads can run concurrently and independently within the same process, allowing for parallel execution of code. And this feature is critical in some programs. For example, a program may present a user interface to the user and also be required to do work in the background, and having the ability to run code in parallel would allow the user interface to remain responsive while background workers within the process can concern themselves with other tasks, perhaps like writing to disk or retrieving information from the internet. A process is created using the fork system call, whereas a thread is created using the pthread_create call. Under the hood, both of these are using the clone system call, and the clone system call, which we can see here, gives us very fine-grained control over the creation process of a process or a thread, particularly in terms of what resources will be shared. Information related to threads within a process can be found through the proc file system by using proc followed by the PID of the process, task, and then the ID of the thread. And we will look at this in the process and threads example that we will now examine in more detail. In this example program, we have a main section which prints out the process ID and the process name. We then initialize the attributes of 2 threads, and we set various parameters associated with those threads, such as the stack size. We then call a pthread_create function, and we pass it the thread IDs and the attributes, and also a function which will be used to carry out the main body of work associated with the thread. We have a section then that destroys the threads and waits for them to join back to the main process before the program exits. The thread function itself just prints out various properties associated with the thread, such as the thread name, the stack size, and various other properties and attributes that we can examine through the proc file system. The threads then wait for a flag to be set, which we will set by pressing a key before they exit. Once the threads exit, the main program waits for them to join back into the main process, and then the overall program exits. Looking at our main program running now, we can see the process ID and the process name being printed out. And then we can see the various thread ID, thread name, and thread stack size parameters being printed. Using a utility like top, we can observe the main properties of the process and of the threads it contains. So we can observe here the main process ID and then the process IDs of the two threads that we created within that process. And we can see that these map to the information that the program itself printed out. So we can see that a particular PID corresponds to the PID associated with the thread. ELF is a standard binary format supported on various platforms, including Linux. This same format is used by application binaries, shared libraries, kernel modules, kernel and core dump files. The ELF file contains an ELF header along with a number of program-related segments. The text section contains the actual machine code that makes up the program, and this is where the program's executable instructions are stored. It typically includes functions, procedures, and the main program logic. It is marked as executable memory. The data section is used for storing initialized data that is read and written during program execution. It includes variables and data structures that are initialized with specific values. The read-only data section contains data that is read-only during program execution. This section typically includes constants, string literals, and other data that should not be modified by the program. Attempting to modify data in the read-only section can result in runtime errors. The debug info section contains detailed debugging data used by debugging tools and symbolic debuggers to map compiled code back to the original source. The ELF header serves as the entry point for parsing and loading the ELF file, and the kernel uses the runtime information from this program header to create the process and then to map the various segments into memory. We will take a more detailed look at the use of the readelf and obj dump utilities in Chapter 3 of this course, but for now we can look at a simple set of commands to dump the header section itself and the main segments of interest to us. For this example, we will use the Hello World program, which we provide in the examples, and I will use a simple script to dump the various sections and the ELF header itself. And here we can see the ELF header itself. It has information on the machine type and the program was built on. It has entry point address, and it has indicators of the size of the header and of the various program headers. And we will look in more detail at readelf and what we can learn from a program using readelf in later slides. We can now look at the various sections which we are dumping with object dump. Here we are viewing the text section, and then the contents of the read-only data section. In this instance, we see the hello world string, which we will print out. And now the contents of the data section, the main data section. And then finally, we can look at the contents of the debug info section. Shared libraries, which normally have the extension .so, are collections of precompiled code that can be shared amongst multiple programs. They bind dynamically with the application at runtime. Shared libraries allow different programs to use the same code without having to include that code in each separate executable. This can save disk space and memory, since multiple programs can use the same library without having to load multiple copies of the code into memory. The kernel loads the application binary into Userspace, as defined in the ELF file, and parses the .int section to find the dynamic linker. ld-linux.so is the dynamic linker loader for the Linux operating system. It is responsible for resolving dependencies between shared libraries and executable files at runtime. When a program is compiled, it includes references to the shared libraries it needs. At runtime, the operating system's dynamic linker loader, ld.linux.so, loads the shared libraries into memory and resolves the references from the program to the library. This allows the program to use the code from the library as if it were part of its own code. Some examples of commonly used shared libraries in Linux include libc, which provides basic C functions, and libpthread, which provides support for multi-threading. Shared libraries are searched in the following paths. rpat is an attribute embedded in an executable binary or shared library during compilation or linking. It specifies one or more directories to be used as search paths for locating shared libraries at runtime. It can be set by the developer when compiling a binary or by using linker flags like -rpat or -rpat-link. We can also set a search path with the ld_library_path environment variable. Runpath is also an attribute embedded in an executable binary or shared library. It serves much the same purpose as rpat, specifying search paths for shared libraries. It is a more recent feature and is considered to be a more flexible and controlled way of specifying search paths. Unlike rpat, it doesn't inherit search paths from the environment or system settings like ld_library_path. Directories listed in the file ld.so.conf are on modern systems in the directory /etc/ld.so.conf.d can also be used to specify the location of shared libraries. The default system libs are also searched, and these are typically /lib and /user/lib. These directories contain system-wide libraries that are installed by the operating system or specific distributions. On 64-bit systems, these are normally called /lib64 and /user/lib64. Finally, user local lib and user local lib64 are directories that normally contain locally installed libraries that are not part of the system-wide installation. We are now going to look at the Hello World shared library example, and this is a simple example to show you how to link a shared library to another piece of code. The example we provide has two simple functions that print messages to the screen, and we have a header file which just has those function definitions. To build this library, we will be using CMake, which stands for Cross-Platform Make. It is an open source build system and build configuration tool, and it is used to manage the process of building software from source code into executables. CMake is designed to be platform independent and is widely used for C and C++. We will be using a CMake list.txt file, which will help us to specify how we want to build our shared library. So now we will look at the various sections of the CMake file. We have a section that identifies the source code we will use, the header file, a directive to build the library itself, an option to include any additional include directories we may need to reference. We can set properties on the library. In this case, we're setting a version number. We can also specify where we want to install the library and where we want to install any header files associated with the library. We can now create the necessary make files by invoking CMake in the current directory. And this, as you can see, creates a make file for us and other associated files which will be used by the make system. We now turn our attention to the example linking shared library, which is a piece of code which will simply call one of the functions in the shared library. So in this code, we include a reference to the shared library's header file, and then we call the function from the shared library itself. We again use a CMake list.txt file to build this particular example. We include a reference to the main.c file, which will produce a binary linked _shared _library _example. And then we link that binary to the actual shared library itself using the target link library directive. We can use a find library directive to locate our library by providing the library name and suitable hints that the CMake system will use to locate the library. We can then again invoke CMake in the directory to generate the necessary make files, and then we type make to build the executable itself. And we now have a executable, and we can use readelf to check which libraries this executable is dependent on. And we see in this instance that there is a dependency on the library we created earlier, and of course the standard libc library. We can now run this library, and as expected we see the printout from the shared library that we built in the previous step. The scheduler is a core component of the Linux kernel responsible for allocating CPU time to processes. It is responsible for deciding which processes or threads get to run on a CPU core at any given time. It does this by assigning a priority to each process based on various factors, such as the amount of time it has already used, the amount of memory it is using, and its scheduling policy. We will look at these factors in more detail in the next slide. The scheduler in the Linux kernel can be called by various events that require a change in the execution context. The time quantum represents the amount of time a process is allowed to execute on the CPU before the scheduler may preempt it and give the CPU time to another process. When the process time slice expires, the scheduler will be invoked. A process may become blocked waiting for an event, such as I/O completion, a signal, or a lock acquisition. This causes the scheduler to select another process to run. When a process completes or is terminated, the scheduler will reschedule existing processes. A software or hardware interrupt can cause the scheduler to be invoked and then possibly select a different process to run. When an interrupt occurs, the kernel interrupts the currently executing code to handle the interrupt request. When a process is forked or a new program is executed, the scheduler may be called to select a new process based on priority. In addition to being switched out by the scheduler, a process can also voluntarily yield the CPU by calling a scheduling function like shed_yield. A program can set its own scheduling policy with the call shed_setScheduler. We can query and set CPU scheduling parameters with tools like schedtool. We can set the CPU affinity of a process with a utility like taskset. We will now look at a scheduling example. We are now going to look at a simple piece of code that allows us to set the scheduling policy and the priority for a task inside a program. In the sample code we've provided, we have summarized the various scheduling policy options you have available, but for this example we are going to use shed_FIFO, and this is typically used in real-time systems and applications where meeting strict deadlines and deterministic behavior is crucial. One does need to exercise a certain amount of caution when setting the scheduling policy and priority for a specific task, as it can impact system behavior. In this program, after setting the scheduling policy, we simply wait for a key press and then yield before terminating the program. After running our program, we can then obtain the process ID and run the shed tool, and this will give us a summary of the scheduling policy, the priority, and also the CPU affinity, which we will look at shortly. We can also use the task set utility to determine the CPU affinity of a particular process. Task set also allows us to assign a new CPU affinity to a process, and we can do this by specifying a bit mask that indicates which cores that particular process should run on. A bitmap of 3, for example, would indicate that the process will run on CPU cores 0 and 1. Context switching is a mechanism used by the operating system to switch between different execution contexts in order to allow multiple processes or threads run concurrently on a single CPU. The context of a process includes CPU registers, program counters, stack pointer, and other relevant information. The scheduler selects the next process from a run queue and updates its scheduling information accordingly. The current execution of a running process is saved on the kernel stack. To view the total number of context switches that have occurred, we can use vmstat-s. In the diagram above, we can see a context switch between two threads. The struct CPU_context typically includes the values of CPU registers, the stack trace, the program counter, and other relevant processor-specific state information. These values are saved when a task is preempted, allowing the kernel to later restore them when the task is scheduled to run again. The sequence involved in the context switch process is as follows. The scheduler restores execution of a selected process from task_struct data structure. The selected process's scheduling information is updated, such as its priority and virtual runtime. The control is returned to the restored process, allowing it to continue execution from where it left off. The scheduler uses various scheduling policies and algorithms to make scheduling decisions based on the state of the system. The completely fair scheduler, CFS, uses a red-black tree to maintain a sorted list of processes and assigns virtual runtime to each process to calculate priority. The red-black tree is a self-balancing binary search tree that allows for efficient insertion, deletion, and lookup operations while keeping the tree balanced. Real-time scheduling provides strict timing guarantees and includes FIFO and round-robin scheduling. Real-time scheduling assigns fixed priorities to tasks or processes, and each task is given a priority value, and tasks are then scheduled based on their priority levels. Higher priority tasks are executed before lower priority ones. Deadline scheduling provides soft real-time guarantees by ensuring processes meet their deadline. In deadline scheduling, each task specifies its own deadline along with an execution time estimate. The scheduler dynamically assigns priorities based on the relative urgency of tasks with respect to their deadlines. Multi-level feedback queue (MLFQ) scheduling divides runtime into multiple priority queues, and it promotes or demotes processes between queues based on CPU usage. And finally, round-robin scheduling assigns a time quantum to each process, and each process is scheduled to run for its allocated time quantum or time slot. Once the time quantum is exhausted, the process is preempted and then moved to the back of the run queue. A system call is an interface which allows Userspace to request kernel services. Read, write, and lseek are some of the most common system calls. These system calls allow user processes to request privileged operations and interact with the hardware through the kernel. On x86 systems, a special instruction hexadecimal 80 is executed from the system call to generate an exception and switch the execution mode from the user mode to the kernel mode. On ARM, executing a supervisory call instruction generates a supervisor call exception, and it fulfills a similar function. System calls are vectored and identified by their numbers. In the case of ARM, these definitions can be found in unistd.h. To invoke a system call in C or a similar language, you can use a library function, for example, open, read, or write, provided by the C standard library. These library functions internally invoke the relevant underlying system call. One useful tool for examining system calls made by a running program is strace. To illustrate this, we're going to take one of the sample programs we provide and run it using strace. This should then allow us to examine the underlying calls made by the program. So we invoke strace and then pass it the program name. And we can then see the output from strace. In the first instance here, it's showing us that the execv system call was made, and this is always used to execute a new program. We can see a brk call, which is related to memory allocation. Some mmap calls, which are used to allocate memory mappings. The access call checks if a file exists and if it's readable. In this case, it's looking for the file's preloader and reports that it doesn't exist. We have an openat call, which opens the file. We have a read call, and this reads data from the open file, in this case, libc.sol.6, which is a shared library file. We see some mprotect calls, and these calls modify the protection of memory regions, making them readable. And we have a prlimit64, and this is a system call that's used to set resource limits for a process. We have some calls to unmap the memory regions we mapped earlier. And we have a call here that retrieves file or file system status information. So as you can see, the strace utility does provide quite comprehensive insight into the underlying calls that are being made by your program. And this can be very useful if you are dealing with a program that you do not have source code for, and you are just curious about what underlying calls it is making. Exceptions are events that occur within the processor itself that require the attention of the operating system or kernel. Examples of exceptions include invalid memory access, divide by zero errors, syscall execution, and other errors that occur as a direct result of the currently executing instruction. There are generally three types of software exception: false, traps, and aborts. When an exception occurs, the processor stops executing the current task and transfers control to the kernel. The kernel can then handle the exception appropriately. To do this, the kernel uses an exception vector table, which contains function pointers to exception handlers. The table is set up during kernel initialization. Interrupts are external events that can happen at any time. These events could be, for example, data being received from a network card or a key being pressed on the keyboard. Interrupts are asynchronous, and they can occur at any time irrespective of what the processor is doing. When an interrupt happens, the processor stops the current task and hands over control to the kernel to execute the corresponding interrupt service routine. The Linux kernel uses an interrupt descriptor table, or IDT, to map hardware exceptions to their corresponding handlers. Each entry in the IDT points to a specific exception handler function. The kernel handles interrupts by saving the current task state. It then services the interrupt and then returns to the interrupted task. Linux provides information on interrupts through the proc file system, and specifically the proc/interrupts interface. The interrupt handler runs in an interrupt context, which is a restricted execution context. In interrupt context, certain operations like blocking or sleeping are not allowed because these operations could lead to deadlocks or other related issues. Interrupt handlers usually run very quickly and perform only the essential operations necessary to service the interrupt. In Linux, nested IRQs or interrupts are not supported. Deferred interrupt handling is a technique used to handle interrupts that cannot be serviced immediately by the interrupt handler. It allows the processor to return to executing the interrupted task as quickly as possible while still ensuring that the interrupt is eventually serviced. The mechanisms provided in the kernel to handle deferred interrupt handling includes work queues, soft IRQs, and tasklets. Kernel threads in the Linux kernel are lightweight processes that operate independently of Userspace processes. K-threads can be created using kthread_create, which clones the thread from kthread process. It is often useful for the kernel to perform some operations in the background, and the kernel accomplishes this via kernel threads standard processes that exist solely in kernel space. The significant difference between kernel threads and normal processes is that kernel threads do not have an address space, and if one was to examine task_struct we would find that it is null. Kernel threads can perform blocking I/O operations without affecting other processes or threads. Examples of kernel threads in the Linux kernel include kworker, ksoftirq, and kswapd. Kworker is a kernel thread responsible for handling general purpose kernel tasks. ksoftirqd is a group of kernel threads that can handle soft IRQs, which are a type of high priority interrupt handling mechanism. And kswapd is a kernel thread responsible for managing swap space. Work queues in the Linux kernel execute non-time critical tasks asynchronously via a dedicated kernel thread called a worker thread. They run in process context, and blocking calls like sleeping are allowed. Interrupts are enabled in work queues. A work item is a unit of work that is submitted to a work queue. Work items are represented by a struct called work_struct and contain a callback function pointer. Execution of work items is queued and managed by the kernel thread. Soft IRQs, or soft interrupts, are a mechanism in the Linux kernel used for handling deferred interrupt processing. Soft IRQs run in interrupt context, and sleeping is not allowed. Interrupts are enabled while running soft IRQs. Soft IRQs are statically defined at compile time and cannot be changed dynamically. nr_soft IRQs is a constant in the Linux kernel that defines the total number of software interrupts available in the system. Soft IRQs are reserved for the most time-critical tasks such as networking and input and output to block devices. Tasklets are a type of soft IRQ handler used in the Linux kernel for handling non-time critical tasks. They run in a soft IRQ context. Tasklets are implemented on top of soft IRQs. hi_soft IRQ is a high-priority soft IRQ in the Linux kernel that runs on every CPU when it is scheduled. It is designed for high-priority work like tasklets that need to be done as soon as possible. When a tasklet is scheduled, it is executed in the tasklet_soft IRQ context, which is a type of soft IRQ designed specifically for handling tasklets. tasklets can be dynamically allocated and initialized at runtime using the tasklet_init function. Tasklets of the same type are always serialized. In other words, the same type of tasklet cannot be executed by two CPUs at the same time. However, tasklets of different types can be executed concurrently on several CPUs. This slide provides some of the references we used in researching this section. We will also use this opportunity to review some of the topics we covered. This section focused on the Linux operating system architecture, and we looked at the basic architecture, the distinction between user mode and kernel mode, and we also saw how the address space is mapped in a 32-bit and 64-bit Linux system. We introduced the concept of virtual addressing, virtual memory areas, kernel logical addressing, and kernel virtual addressing. We also looked at how these concepts impact user space and looked at the role of MMUs, or memory management units. We discussed page faults and how they are handled in modern systems. And we looked at the concept of shared memory, memory mapping, and introduced the concept of processes and threads. We investigated the ELF file format and introduced a range of tools for analyzing this. And we evaluated examples for shared memory, scheduling, context switching, and system calls. We looked at interrupts and exceptions, and also looked at some kernel features like work queues, threads, software queues, and tasklets. You have covered quite a lot of material in this section, and understanding it is vital for the sections that follow. So please take your time to review the material, work through the examples, and try out the various investigative tools that we have introduced.
This section of the course is dedicated to discuss basic Linux monitoring tools at our disposal to understand the state of the system. There are various monitoring tools available with Linux which can help monitor system performance, resource utilization, and other aspects of the system. Linux kernel exposes the system information through pseudo file systems such as procfs, sysfs, and devfs. These tool fetches the system information from various files available in the pseudo file system. Let's understand the pseudo file system and the available monitoring tools in detail. In this video, we are going to discuss the pseudo file system. In Linux operating system, pseudo file system is a virtual file system that do not correspond to any physical storage device or represent any actual file. Instead, it provides a virtual interface for accessing and manipulating the kernel data structure, system information, and various system resources. Some of the common examples of pseudo file systems in Linux includes proc file system. This is to access the process and system information. Sys file system to access the information related to the system hardware, devices, and drivers. Dev file system. This is device file system to access the device available in the system. Temp file system used to store the files temporarily in a volatile memory, usually RAM. Debug file system exposes the debugging and the tracing information to user space. The proc file system is a virtual file system in Linux that provides an interface to access the process-related information and system configuration-related information. Each process is represented as a directory under /proc with a unique process ID. For example, if a process has a process ID as 978, the corresponding directory will be named as 978 under the proc file system. Inside each process directory, there are various files that provides the information about the process, such as its command line argument, environment variable, status, memory usage, and file descriptors. The proc file system also includes the files and directories that provide system-wide configuration and information parameters, such as CPU usage, memory usage, the loaded modules, interrupts, file system statistics, etc. The information available in the proc file system is dynamically generated and updated by the kernel in the real time. This information is used by the system utilities, diagnostic tools, monitoring application to provide a view about the system's current state. Now let's take a look at the important files and the directory in the proc file system. CPU info provides the information of the processors available on the system. Meminfo provides the memory information of the system. Load average file provides the average system load. Version file provides the Linux kernel version. File system provides the file system supported by the available kernel. Command line file provides the kernel command line argument passed during the kernel boot up. PID status file provides the information regarding the process. And the map file provides the information regarding the process memory map. There are many more which we can refer to the man page of proc file system to get more details around the important files available in the proc file. Now let's take a look into the live system how these files look like. The CPU info file identifies the type of processor used by the system. As we can see, it provides us the number of processor used in the system along with its associated configuration. Meminfo file reports valuable information about the system RAM usage. Parameters like memory total represents the total amount of physical RAM in kilobytes. Memfree represents the amount of physical RAM in kilobytes left unused by the system. Buffers represent the amount of physical RAM in kilobytes used for the file buffers. Cached represents the amount of physical RAM in kilobyte used as cache memory. Swap cached, the amount of swap in kilobytes used as the cache memory. And similarly, many more other parameters which helps us to get a detailed view of memory usage. Load average file provides a look at the load average in regards to both CPU and I/O over time. The first three columns measures CPU and I/O utilization of last 1, 5 and 10-minute period. The fourth column shows the number of currently running process and the total number of processes. And the last column represents the last process ID used. The file system file provides the information about the supported file systems by the Linux kernel. In the first column, we can see no dev, which signifies the file system is not mounted on a device and it's a pseudo file system. And in the second column, lists the name of the file system supported by the kernel. Sys file system. Sys file system provides a view of system's hardware, devices, drivers, and kernel modules. It is organized hierarchically with each device and driver represented as a directory. It exposes the information about devices such as their attributes, status, and configuration parameter. Files in sys file system are organized in such a way that each directory corresponds to a specific kernel feature, configuration option, or hardware device. Let's take a look. The block directory contains devices like hard drives, exposing the storage related settings and the information. Sys bus directory represents the system buses such as PCI, USB, providing access to the devices connected to those buses. Sys class organizes devices by their class or type, making it easier to manage common attributes and settings. Sysdev, a directory used for maintaining the device-specific directories, correspond to the devices dynamically created by the kernel. Sysdevices holds directories representing various devices in the system, offering configuration and information interfaces. Sysfirmware contains the firmware-related information and interfaces for the system firmware. Sysfs provides information about various file systems and their properties on the system. The kernel directory holds specific kernel setting and information for interaction and configuration. The module directory offers details and configuration about the loaded kernel module. So let's say, as an example, we want to check the battery status. We will navigate to sys class power supply bat0. This directory will provide all the information regarding the available battery. For example, we want to check the status of the battery. and it is discharging at the moment. The dev file system, also known as the device file system, is a pseudo file system in Linux that provides a way to access devices as if they were the regular files. It acts as an interface between the user space applications and the kernel device drivers. Dev file system allows processes to interact with the devices using the standard file operations such as read, write, open, seek, etc. This way, the dev file system provides a standardized and uniform way for application and user to communicate with devices regardless of the underlying hardware or device types. The dev file system is typically managed by a combination of udev daemon and the dev tempfs file system. Now let's take a look at the dev file system and its file organization. Running ls-l provides us with the file details, and we can determine the device type by examining the first character associated with the file listing. For example, uh, the C represents a character driver, whereas the B represents a block driver. Furthermore, devices files in dev often have a specific naming convention to indicate the device type, such as /dev SDA represents a block device or a SCSI disk, or /dev TTY represents a serial terminal, whereas /dev TTY USB 0 for a USB serial port. The debug file system provides a mechanism for kernel developer to expose debugging and the tracing information to user space. It is primarily used for debugging and troubleshooting purpose. Debugfs is typically mounted on syskernel debug mount point, and it can be enabled in the kernel using the config debugfs configuration option and mounted in user space using the given command. Commonly, it is used by perf, ftrace, dynamic debugging, and kernel debuggers. So far, we have talked about the pseudo file systems and discussed various pseudo file systems available in the Linux operating system. In this section, we are going to discuss the tools available in Linux that uses the pseudo file system to either provide information to the user or configure the system in a specific way. Linux provides several monitoring tools available that can help monitor system performance, resource utilization, network activity, and various other aspects. Here is the list of commonly used Linux monitoring tools. For process monitoring, we have PS, top, htop, PS3. For memory monitoring, free vmstat, pmap are useful. For disk monitoring, iostat, iotop can be used. For scheduler, mpstat can be used. For the networking section, netstat, tcpdump, ethtool are some commonly used tools. The given image is taken from Brendan Gregg's blog post. It provides a detailed view of each component of the Linux operating system and associated monitoring tools. I encourage you to pause the video for a moment and familiarize yourself with the Linux OS components and associated toolsets. Before diving into the toolsets, let's understand the nuances of the memory representation in these tools. Most tools represent the memory using various classifications, and it is important to understand the difference among each classification. For example, VSS or virtual set size represents the total virtual memory usage of a process, including the shared and the private memory. Whereas RSS or resident set size represents the total physical memory held in the physical RAM, including the shared library. USS or unique set size represents the physical memory held in the physical RAM, excluding the shared library. Please note down the difference between the RSS and USS. Both represents the physical memory, but RSS includes shared library and USS excludes the shared library. PSS or proportional set size is the estimate of physical memory of process, including the proportionate shared memory. PSS divides the shared memory equally among the processes sharing it. Memory usage wise, VSS is the highest, followed by the RSS, which is greater than the PSS memory. and the USS is the least memory usage. We will now explore the tools available for the process management. The first tool we are going to discuss is process status, or commonly known as the PS command. PS is a command line utility used to display active processes and their attributes. It is one of the most commonly used commands and is essential for the process management and troubleshooting. PS displays process ID, its parent process ID, CPU usage, memory usage, process status, etc. The provided example offers a snapshot of the active processes in the system. A significant amount of information is visible in this snapshot. Let's attempt to comprehend the significance of each parameter associated with the process. User represents the user or owner of the process. PID represents the process ID, a unique identifier for each running process. %CPU represents the percentage of CPU usage by the process. It is the CPU time used divided by the time the process has been running. %memory represents the percentage of RAM usage by the process. It is the ratio of the process's RSS memory to the physical memory on the machine. VSG represents the virtual memory size of the process, whereas RSS, we already discussed, indicates the portion of memory held in the RAM, including shared library. TTY states the terminal type associated with the process. Stat represents the status code indicating the status of the process, whether the process is sleeping, running, or idle. Start represents the start time of the process. Time represents the cumulative CPU time consumed by the process. And finally, the command represents the program being executed by the process. If you look further in the command, kernel threads are represented in a square bracket, whereas the user space application represented as is. There are many ways the process status can be represented, along with the information it displays. In this particular example, we are using the command line option AUX. I encourage you to read the man page to get more details on the usage of the PS command. The next tool in our list is the top command. Top command is a utility that provides real-time monitoring of the system processes, CPU usage, and memory usage. The main difference between the top and the PS is that top provides a real-time dynamic view of the processes, whereas the PS provides a static snapshot of the processes at the moment it's run. Let's take a look at a live example. In this example, we are using -d command line option to specify the delay between the updates. For this example, it is set to 1 second. As you can see, the process table is getting updated every 1 second. Let's understand the information available in the top output. System time represents the current time of the system uptime, and the number of users logged in. Load average, we already discussed about it in the proc file system section. It provides the load average of last 1, 5, and 15 minutes. Task represents the total number of tasks in the system, and out of which how many are running, sleeping, stopped, and in zombie state. CPU percentage is divided into various sections. Let's understand each section. US represents the user space, or the percentage of CPU time spent on the user space processes such as applications. SY represents the system space, or the percentage of CPU time spent on the system processes such as kernel operations. NI represents the nice value, that means the percentage of CPU time spent on the processes with a positive nice value that indicates a lower priority task. ID represents the idle state, or the percentage of CPU time that is idle and not performing any task. WA represents the IO wait, or the percentage of CPU time waiting for an input output operation to complete. HI represents the hardware interrupt or the percentage of CPU time spent on servicing the hardware interrupts. SI represents the software interrupts, that means the percentage of CPU time spent on servicing the software interrupts. ST or steal time is the percentage of CPU time stolen by a hypervisor from a virtual machine running on the system. It is only applicable in a virtualized environment. In the memory section down below, we have the memory statistics for total memory, free memory, used memory, and the buffered or cached memory. Similarly, for the memory statistics for the swap space, we have the statistics for total memory, free, used, and the available memory. In the process header, PID represents the process ID or unique identifier of the process. User represents the user which owns the process. PR represents the priority of the process. NI represents the nice value of the process. Virtual represents the virtual memory usage. RES represents the residence memory usage. SHR represents the shared memory usage. S represents the process state, whether it is running, sleeping, idle, or in zombie condition. %CPU usage represents the CPU usage. %memory represents the memory usage. The time indicates the total accumulated CPU time, and the command represents the command used to start that process. There are many command line options available in top command. Do refer its man page for more information. The next command we will look into is process tree or PS tree. PS tree is a command line utility that displays a tree-like representation of the running processes showing their parent-child relationship. If the PID is mentioned, the tree is rooted at the PID. Otherwise, it is rooted at the init process. In the example below, we are dumping the call chain of PID 3072. While debugging, it is helpful to track the calling chain of the processes. In this section, we will explore the tools for gathering memory-related insights. Free is a command line utility that provides information about system memory usage, including the total used and free memory. It uses the underlying file system proc meminfo file to get the memory information. Let's look at the sample output of the free command. Total represents the total amount of physical RAM installed on the system. Used represents the amount of memory currently used by the various processes. Free represents the amount of memory that is not in use by any process and is readily available. Shared represents the memory used for the shared memory segment, which allows processes to share memory. Buffer or cached memory is used by the kernel for buffering and caching. This includes file system buffering, page caching, etc. Available indicates estimate amount of memory that can be allocated to the new process without swapping. This takes into the account the total free memory as well as the memory that can be quickly reclaimed from the buffered and the cache pools. vmstat or virtual memory stat is a command line utility to display the virtual memory statistics, including the information about system memory, processes, paging, block I/O, CPU usage, and more. In our example below, we are using 6 snapshots of vmstat at 1 second interval. Let's take a look at the live example. In this command, we are using the arguments 1 and 6, which means the vmstat will dump 6 snapshots at the interval of 1 second each. Now let's dive into the information represented by the vmstat. Procs represent the information about the processes, whereas R represents the number of processes in running state, which is using the CPU, and B represents the number of processes in uninterruptible sleep states, which is basically waiting for an IO to happen. The memory section represents the statistics about the memory which we already discussed, such as swapped memory, free, buffered, and cached memory. The swap column represents the swap space statistics, wherein SI represents the amount of memory swapped in from the disk, and SO represents the amount of memory swapped out of the disk. The IO section represents the IO related statistics, wherein BI represents the block received from the block device, and BO represents the block sent to the block device. In the system section, we have the system level statistics, wherein in represents the number of interrupts per second, and CS represents the number of context switched happened per second. In the CPU section, we already discussed about the breakup of US SYID in the top command. So I don't think so it is necessary to discuss again in this section. Now these parameters provides insights into the different aspect of the system performance and the resource utilization, helping us to understand how process, memory, swap, IO, CPU are interacting on the system. The next command we will discuss is the pmap command or process map command. Pmap is a command line utility that provides detailed information about the memory mapping of a process. It uses the maps file to gather the virtual memory information of a given process. In the given snapshot here, we use the pmap command to dump the virtual memory information of our memory example, and to enhance the clarity, we condensed and annotated this snapshot. The top line here represents the process ID and the name of the program. The address column represents the start of the virtual memory segment. The kilobyte column represents the amount of the virtual address space reserved for that region. RSS again represents the amount of physical RAM that is currently being used by the particular memory region, and it includes the shared memory region as well. The dirty column represents how much memory the region contains with the modified data that has not been written back to the disk yet. This value is also expressed in kilobytes. The mode column displays the access permissions and the flags associated with that particular memory region. It shows whether the memory is readable, writable, executable, or whether it's the shared or private memory. The mapping column provides the information about the type of memory mapping that has been established for the memory region, whether it is a file-based memory mapping or a memory-based memory mapping. There are various virtual memory segments shown in the given snapshot. For example, these segments are associated with the memory program itself. Further down, the libc segment represents the libc shared library, which is loaded as a dependency in this program. Similarly, the LD Linux represents the dynamic linker loader used in the Linux system to load and link shared libraries when executing a program. The anon or anonymous represents the section of memory region that are not backed by any file. These regions are typically used for program stack frame, heap memory, or memory allocated for the runtime data structure within a running process. Furthermore, the read-only segment of the memory program represents the program's private section containing constants, etc. The read executable segment represents the executable code segment. The anon section here represents the heap segment of the process. I referred to the maps file to confirm the heap segment. Moving down, we encounter the read-only segment of libc shared library, followed by its read executable segment. The stack represents this process stack frame. Using pmap, we can obtain a comprehensive view of the virtual memory segment placement and the loaded shared library. This is highly beneficial for debugging a program. In the preceding sections, we covered tools pertaining to process and memory. I trust you are following the slides and learning as we progress. In this segment, we will delve into the tools for monitoring CPU and I/O activities. IOStat tools monitors and reports the IO statistics of disk controller, and the file system performance. It is useful to understand system-wide input-output load using metrics like disk utilization, input-output rates, throughput, and the response time. The example shows a snapshot of the IOStat command. Here, the average CPU section represents various CPU utilization percentages. User represents the percentage or the amount of CPU time spent in a user level process. It represents the time the CPU spends executing user application and tasks. Nice represents the percentage of CPU time used by a process with a nice value. The nice value is a priority adjustment that affects the CPU scheduling. Processes with a lower nice value have higher priorities, and this column shows the CPU time spent executing tasks with the adjusted priority. System represents the percentage of the CPU time used by the kernel or system processes. It is the time which included the system calls, managing hardwares, and other kernel level operation. IO wait represents the percentage or the portion of the CPU time that is waiting for input-output operations to complete. It is an indicator of how much time the CPU spends idle due to a pending disk or IO operation. Steal represents the percentage or the time the hypervisor or in the virtualized environment steals from a virtual machine's CPU usage to serve other virtual machines. It is relevant in the virtual environment where multiple virtual machines share the same physical CPU. Idle percentage represents the CPU time where the portion of the CPU is not actively executing any task. It is a measure of how much capacity the CPU has left for the additional work. The next section provides the information about the input-output activity of the devices such as hard drive or the storage device. Here's what each term signifies. The device column represents the device that are being monitored. It could represent a physical or logical device such as a hard drive as in /dev/sda or /dev NVMe 0N1 which represents a physical hard drive or other block devices. Loop represents a logical device and it is often referred to as a loopback device. It is a virtual block device in Linux that allows you to treat a regular file as if it were a block device, such as a hard drive or a partition. This provides a way to mount the file system that resides within the regular file, as well as perform various other tasks involves block device using these files. TPS or transaction per second is the value that indicates the number of I/O operation reads or writes that are issued to the device per second. It gives an overall count of I/O operation, and in this example, as we can see, our hard drive, SSD hard drive NVMe 0N1 is getting 10.56 transactions per second. Kilobyte per read per second is an indicator or matrix which represents the amount of data read from the device per second. It is measured in kilobyte. It provides information about the rate at which the data is being read from the device. And similarly, kilobyte write provides an indicator where the data is getting write into the device per second. Kilobytes discarded per second is an indicator which represents the amount of data which is discarded or removed from the device per second. It is also measured in kilobyte, and this is relevant for devices that support discard or trim operations such as SSD. Kilobyte per read is the total value or the cumulative of the total data read from the device since the IOStat tool started monitoring it. It is measured in kilobytes. And similarly, kilobyte write is the cumulative total data that is written into the device since the monitoring begins. Kilobyte discarded count gives us a cumulative total of the data discarded from device since the monitoring began. It is also measured in the kilobytes. The significance of this section lies in understanding how devices are being utilized in terms of I/O operation. The TPS value gives an overview of the workload, while the kilobyte read and kilobyte write per second value indicates the rate of data flow to and from the devices. The cumulative sections, kilobyte read, kilobyte write, and the kilobyte descriptor, that provides an overall perspective on the amount of data processed by devices since the monitoring started. This information is very crucial to perform the performance analysis and identifying the potential I/O bottlenecks. IOTop tool is used to monitor the real-time I/O statistics on a per process basis. It helps identifying the process generating high input-output load and causing the performance issues. IOTop metrics includes the total I/O, read and write rates, and the I/O priorities. In summary, IOStat provides the system-wide disk I/O statistics and is more focused on overall system performance analysis, while the IOTop is used to monitor the real-time disk I/O activity on a per process basis, helping us identifying the specific processes that may be causing the I/O bottleneck. Depending on the monitoring needs, we may use one or both of these tools to gain insight into the disk I/O performance. MPStat or multiprocessor statistics. This tool helps us in monitoring the individual CPU core usage using the metrics like user, system, and idle time, as well as the other statistics like interrupts and the context switches. Use case wise, it is useful to identify the CPU bottleneck, load imbalances, and the overall CPU performance. In the example below, the first row indicates the overall CPU usage and the rows below indicates the statistics of the individual CPU cores. MPStats provides an enhanced CPU usage indicators. Let's discuss the significance of each indicator. Percent user, as we already discussed in the preceding slides, it's the column shows the percentage of CPU time spent executing the user level processes. It includes the time spent running applications and user initiated tasks. A high percent user value indicates that the CPU is primarily being used for the user level activities, which is typically for the most computing tasks. Percent nice, the column represents the percentage of CPU time spent running user level processes with a positive niceness value. And in Linux, the nice value influences the process priority, with the higher value indicates a lower priority. Percent system represents the percentage of CPU time spent in kernel level system processes. It includes the time spent handling system calls and managing hardware. High percent sys value can indicate that the system is under heavy load due to the system level activities, potentially causing the system services or the kernel tasks. IO weight represents the column where the percentage of CPU time spent waiting for an IO operation to complete. It indicates the time when the CPU is idle because it's waiting for the data to be read or written from the storage device. Again, a high IO wait value may suggest that there is a IO bottleneck somewhere and the CPU is frequently waiting for the data from the storage. In this condition, we should look at the IO stat or IO top to identify the IO bottleneck. Percent IRQ or interrupt service request. This column represents the percentage of CPU time spent on handling hardware interrupt service requests. Interrupts are the signal generated by the hardware devices to get the CPU attentions for the various tasks such as processing IO request. We discussed the interrupt in our module 1. A high percent IRQ value can indicate that the system is handling a significant number of hardware interrupt, which may be a sign of heavy IO activity or issue with the hardware devices. Percent soft or the soft IRQ. So the soft IRQ we already discussed in module 1 of this course, and the significance of the percent soft IRQ CPU usage indicates that the CPU time being spent handling the software interrupt request. Software IRQs are similar to the hardware interrupts, but are generated by the kernel in response to a specific event, such as network packet processing or the timer event. Again, a high soft IRQ value may indicate that the kernel is performing intensive background task, possibly due to the network activity or other kernel related work, which includes a soft IRQ. Steal, as we already discussed in our preceding slides, it's the percentage, or the column represents the percentage of the CPU time that a virtual machine running on a hypervisor and has been waiting for the CPU resources on the physical host. In a virtualized environment, a high steal value suggests that the virtual machine is contending with other VMs for the CPU resources on the host. Guest is the column which represents the percentage of CPU time spent on a virtual machine in guest mode, often referred as a VM time. It represents the CPU time used by the virtualized guest and operating system. And a high guest value indicates how much time is consumed by a virtualized environment, which can be helpful for monitoring the performance of the virtual machine. Gnice or guest nice represents the percentage of CPU time spent running a virtual machine with a positive niceness value. Idle, again we discussed in our preceding slides, is the column that indicates the percentage of CPU time is idle and not actively executing any process. A high idle value indicates the CPU has available processing capacity, while the low value suggests that the CPU is actively engaged in a processing task. Now, these CPU utilization percentage provides a valuable insights into how the CPU is utilized for the various type of activities, and it helps administrators and users to monitor and diagnose the system performance and resource usages. Now in this section, we will look into the three essential network monitoring related command line tools: netstat, ETH tool, and TCP dump. This tool provides network administrators with the insight into the connections, interface settings, and the live packet analysis. This command helps in enhancing network performance, troubleshooting, and security. The netstat command, or network statistics command, is used to display the network connection and the routing table. Connection wise, it provides an information about the active connections, listening ports, and established connections. It provides us the statistics related to the network protocols such as TCP, UDP, ICMP, etc. And it also provides the multicast group information. Netstat command utilizes procnet interfaces to provide the network information, and it is helpful to troubleshoot the network connectivity issues, monitoring network activity, and analyzing the network performance. Now let's look at some of the examples of netstat. Netstat-AP displays all the active network connection and the associated processes. It tells us the protocol, the port number, the state of the port number, along with the program which is associated with that port. The next example uses the command line option TULN, and it displays a list of all the listening TCP and UDP ports with the numerical addresses and the port number. Netstat-R command shows the routing table, and netstat-S provides the detailed network protocol statistics. Netstat command works on the TCP IP connection level, whereas the ETH tool command, which we are going to discuss now, works on the network interface or on the network port level. It focuses on querying and controlling the network interface settings and the statistics. It provides the detailed information about the Ethernet device, such as its link status, its speed, duplex mode, and the driver information. ETH tool gathers the statistics on network interfaces performance, such as packet counts and the error statistics. And configuration wise, it allows to configure the features like wake on LAN, offloading capabilities, and the flow control settings. Let's take a look on a live example for the ETH tool. ETH tool command, executed with the Ethernet interface name as an argument, displays the detailed information about the Ethernet network interface, including its speeds, duplex, and the link status. You can get the interface name using IP address show command. eth-tool-s command provides the statistics such as the packet counts and the error statistics for the provided Ethernet interface. TCP dump is a packet capture tool used to capture and analyze the network traffic. It can filter the packet based on various criteria such as hostname filter, which filters the packet based on a host name, port filter, which filters the packet destined to a specific port, for example, port number 80, protocol filter, which filters the packet based on the protocol specified, such as ICMP or TCP or UDP, etc. Source filter filters the packet based on the source IP used in the packet. Destination filter filters the packet based on the destination IP. Protocol flag filter, using this filter, we can filter the packet based on the protocol flags. And in the given example, we are capturing the TCP packets which has the SYN flag set. We can use logical operators to combine multiple filters together to make a meaningful packet capture. This slide provides the references for further reading on some of the topics we discuss in this module. To summarize, we covered various pseudo file systems such as procfs, sysfs, devfs, and debugfs. We also covered important files available in these file systems. We covered different monitoring tools like ps, top, free, vmstat, iostat, mpstat, tcpdump, etc. And we also covered the type of information these tools provides to better understand the state of the system. Monitoring tools are the first level of debugging tools required to understand the state of the system. I hope this module was helpful to better understand the available monitoring tool and their usage.
Welcome to Module 3, where we're going to turn our attention now to application debugging. In this section, we will look at application debugging and the tools that can assist us in doing that. We will look at a number of tools that are collectively known as binutils, and these will include readelf, object dump, object copy, nm, and address to line. We will also look at the tools that provide insights into shared libraries. And then we will turn our attention to the GNU debugger GDB, which is an essential tool for the Linux software engineer. We will cover the concept of optimization, and we will look at how it can influence how we debug. GDB is a powerful tool, and this power can be extended through Python extensions, and we will take some time to examine how that can be done. We will look at various examples like shared memory debugging, segmentation faults, crash reports, analyzing core dumps, and using backtrace analysis. Binutils are a collection of tools we use to work with object files, program files, and libraries. The most commonly used binutil tools are mentioned below, and these include readelf, object dump, object copy, nm, and address to line. We will now look at each of these utilities in a little more detail. Readelf is a command line utility that displays information about the contents of binary files, such as object files, shared libraries, and executables. Readelf is typically used to examine the contents and organization of binary files, specifically ELF, which are executable and linkable format files. It can display information such as the sections and segments in the file, the symbols defined in the file, the dynamic relocations and dependencies of the file, program header information, and version information. Understanding the layout and organization of an ELF file can be very helpful for debugging issues related to memory corruption, alignment, or unattended side effects. We will now look at an example of using readelf to examine the contents of a file. We previously looked at readelf, and readelf allows us to examine a ELF format file We can use it on existing binaries, such as the ls utility shown here on the slide. And we can also use it on code we create and compile ourselves. In this particular session, I'm going to look at the Hello World example that we used earlier in the course. After building the program, we can run readelf-h hello world, and this will allow us to view the elf headers. So viewing the headers of the file then allows us to look at certain summary information about the binary. For example, we can see that it is a position-independent executable file, which means that it can be loaded at any memory address without modification. And this property is particularly useful for security features such as address space layout randomization. We can also view elf sections by using the -s argument. And this prints out the various section headers, which we can see here for our example code. We can, if we wish, then look in more detail at a particular section by using the -x followed by the section name. And in this instance, we just look briefly at the text section of the elf file. One can also use the -a option, which allows us to look at all of the sections in much more detail. So we have the header section we looked at earlier, and then we can look at various mappings, including segment mappings and the symbol tables. Another very useful feature of the ELF program is the ability to determine the shared libraries that the program depends on, and we can do this using the -d option and then grep for needed, which will identify any libraries that we have a dependency on. So all in all then, readelf is a very powerful utility, allowing us to examine an ELF binary in considerable detail. And this can often be very useful for debug purposes where we need to inspect specific aspects of a binary. ObjectDump provides detailed information about the contents and structure of object files, executable files, and shared libraries. It can display assembled machine code instructions, assembly instructions, addresses, and opcodes. It can also display symbol table and function variables, and it can show the reallocation and linking information associated with the program. ObjectDump is a more general purpose tool compared to readelf because it can handle various binary formats, including ELF, COFF, which is the common object file format, and many others. One of its great benefits is that it can be used to disassemble binaries, and like readelf, it can also display sections and provide information about various types of object files. We will now look at some examples of using ObjectDump. So for this series of examples, we're going to use the memory program we visited earlier in the course. So having built the program, we can dump a summary of the program using the -f option, which tells us the format and architecture of the file. One of the real benefits of ObjectDump is to be able to disassemble code, and we can do this with the -d option. And this provides a disassembly of each section. And this can be very, very useful. For example, here we're looking at the main function, and then we can look at individual functions within the program, the first function and the second function. This can be very, very useful for understanding the actual resultant code that runs on the hardware. Like readelf, we can also dump various sections, symbol tables, and other information available in the binary. For example, here in the symbol table, we can see the location of the first function and the second function. And we can also look at how data is stored. In this instance, we can see the global variables which we declared at the top of the program. The nm utility is used to list the symbols from object files, executable and shared libraries. It can show the associated address of the various symbols. In this example, we look at the memory program we created earlier, and we search for the location of the first function. NM is specifically designed for displaying symbol information. It provides a concise list of symbols, including their addresses and types, making it easy to see the layout of functions and variables in a binary. NM is particularly handy for developers and debuggers who are interested in understanding the symbol table of an executable or shared memory. Address to line is a very useful utility for examining kernel oops and crash dumps, and it allows us to translate addresses into file names and line numbers in source code files. In this example here, we take the earlier address we obtained using NM, and we request address to line to identify the line number of the first function, which it does in this instance. LDD is used to display the shared library dependencies of an executable or shared library. It can often be useful for investigating issues associated with shared libraries. If a library is missing, for example, on the system, LDD will indicate this by showing a not found message next to the missing library. LDD provides the absolute paths of the shared libraries. If a library is not found, you can check whether it exists or not in the specified paths. This information can be very important for understanding whether the library is in a standard system location or if it is in a custom path which needs to be specified. LDD can also be useful for investigating library version mismatches. LDD can be used on binaries, as shown in the example here, where we examine the library dependencies of the ls command. We can also use LDD on our example code that we looked at earlier, where we linked a main program to a shared library. You can see in this example that the library we created, my library, is shown in the LDT output, as is a reference to LD Linux 86-64. And this is a dynamic linker loader library on Linux systems used in the execution of dynamically linked ELF files. We also see a reference to linux.vdso, and this is the virtual dynamic shared object library, also used on Linux systems. It is a special shared library that provides a way for Userspace applications to efficiently make system calls without transitioning to kernel mode. GDB is a GNU debugger that supports languages like AD, C, C++, Assembly, D, Fortran, Go, and Rust. It is mainly used to debug a process, which we can debug by starting it with GDB followed by the program name, and core dumps. A core dump is a file that contains a snapshot of the memory of a running process and other relevant information at the time of a program crash or abnormal termination. When a program crashes, the operating system can create a core dump to assist with debugging and diagnosing the cause of the crash. GDB utilizes the debug information present in the ELF file. Dwarf is the debugging file format used in Linux, which allows us to embed debug information in an ELF file. The dwarf format consists of a series of data structures that describe the various elements of the program being debugged, such as functions, variables, and types. Each data structure has a tag that specifies the type of element it represents and a set of attributes that provide additional information about that element. LLVM LLDB is an alternative to GDB. It is a next-generation high-performance debugger, and it is built as a set of reusable components which highly leverage existing libraries in the larger LLVM project, such as CLang expression parser and LLVM disassembler. The .text section of an ELF file typically contains the executable code, that is the machine code that the CPU can execute. The debug sections are separated from the .text section, and this separation allows a binary or an executable to be created without including the debugging information. The binary can be used on the target system for running the program without the overhead of debug information. However, the same ELF can also be used for debugging tools on the host system. We can use the following command to check if debug symbols are present in a binary file. And this is often useful if you have not compiled the file yourself from source code. readelf -debug-dump equals decoded line and then the name of the program. We can also look at the debug sections of the ELF file in considerable detail with readelf-w followed by the program name. Compilation options available for adding debug symbols are as follows. -G0 provides no debug information. -G1 produces minimal information, enough for producing backtraces, but no information on variables or line numbers. -G2, which is the default debug level, and which is the same as just passing -G without an argument, produces symbols and line numbers required for debugging. -G3, which provides extra debug information, also includes macro definition. And finally, -GGDB3 is similar to -G3, but generates debug information that has been tailored specifically for the GNU GDB debugger. In order to accurately trace source code in GDB, we should disable code optimization. The following are some recommendations for doing that. We can use the -O0 compiler optimization flag. We can enable only GDB compatible optimization with the -0G flag. We can use the -G debug flag on its own. And we can annotate a specific function with the compiler attribute option shown here. Removing the static qualifier from a function can prevent the compiler from inlining the function for the purpose of optimization. We can use the volatile keyword to ensure that a variable is not optimized out at compile time. We can also set these equivalents in CMake using the CMake flags directive, an example of which is shown here. We will now look at a optimization example using some of the source code that we have provided with this course. In the optimization folder, you will find a main.c, which is a simple program that illustrates some of the concepts we have spoken about. The first function here uses the attribute we spoke about to ensure that the function is not inlined or optimized out. The second function does not have this attribute, so it can be optimized by the compiler. We will also take a look at the CMake list.txt file, and in this particular file we have made provision for building both a debug version of the code and a release version. In the debug version we're setting little or no optimization, whereas in the release version we use an optimization level of 3. A useful exercise to understand the effects of optimization is to compile the code into assembly, and we can do this with two rules we have added to the CMake file, which builds assembly versions of both the optimized and the non-optimized code. We can then use a tool like Meld or some other tool that can show the differences between the resulting files to examine in more detail the code that is created by the various optimization levels. In this case here, I'm using Meld to show the debug version on the left-hand side and the release version on the right-hand side. And we can see that there's little or no difference in example function 1 because we instructed the compiler not to optimize that function. If we look at example function 2, we can see that there are more significant differences in the resulting assembly code. We will now look at some of the command line options available to GDB. To execute a program with GDB, we can simply type GDB followed by the program binary that we wish to debug. The sysroot directory is the directory in which GDB looks for the location of the source files. And we can set the sysroot location by typing set sysroot and then a path to the actual location. We can also attach GDB to a running process, and we will look at an example of this shortly. But the syntax to use is GDB-P followed by the process ID of the programmer binary that we wish to debug. Once a program has been loaded up into GDB, we can execute that program by typing run. We're now going to take a look at some of these options by debugging a program called segfault. This particular program has been deliberately constructed to create a segmentation fault. So we will build a program and then we will use GDB to load the program into memory. Once the program loads, we can then type run to execute the program. But first we will set the sysroot location to the current directory. GDB will then look in this directory for any related source files. And then we can see, once we run the program, that the segmentation fault occurred on line 7 of the program. And if we wish to see a backtrace, we can also type BT and see the sequence of events that led to the segmentation fault. We can then terminate the program by typing Y and exiting the debugger. We can also attach to a program that is already running. And to do this, we use GDB and specify the process ID of the program that we wish to attach to. We can obtain the process ID by using the ps command, and then having obtained that ID, we simply type GDB-P and the process ID. GDB attaches itself to the process, and now we have the capability to interactively debug the running program. This can be very useful for production systems or for programs and binaries like services and that, which may be started automatically. We can also use the backtrace command to obtain some insight into where the program is at the particular point at which we attach.
A breakpoint is a debugging feature that allows a programmer to pause the execution of a program at a specific point, typically a line of code. When a breakpoint is set, the program will run until it reaches the specified location, at which point it will stop, giving the programmer an opportunity to inspect the program state, variables, and memory. When a software breakpoint is set, the debugger replaces the instruction at the breakpoint with a trap instruction. This trap instruction causes the program to halt execution and enter the debugger. The debugger then provides the programmer with a variety of tools for examining the program state. A temporary breakpoint can be set by using tbreak followed by a line number. The temporary breakpoint will stop once, and then the breakpoint will be automatically removed at that point. A hardware breakpoint
can be set with hbreak followed by the line number. In systems where the code is executed directly from flash memory, non-volatile memory that is, modifying the code in place as is done with a software breakpoint may not be possible or practical. Flash memory is typically read-only during program execution. A hardware breakpoint is a breakpoint that uses a debugging feature provided by the CPU, and this allows one to set breakpoints without modifying the code. The CPU has dedicated registers of resources that can be configured to trigger an exception or interrupt when a specified address is accessed. We will now take a look at an example of setting breakpoints. And for this example, we will use the optimization example code that we created earlier. So we start by loading up the code in GDB, and then we set a breakpoint on a particular line number, number 7 in this case, with B space 7. And then we run the program. And we can see as we run the program that the breakpoint is hit at the desired location. We can also use the backtrace function to look at the sequence of instructions that led us to the breakpoint. If we wish to look at all of the breakpoints we have set, we can use the info breakpoints command, which will list any existing breakpoints. And to remove a breakpoint, we simply type delete followed by the breakpoint number. As we can see, we have now no breakpoints remaining or set. We can also set a temporary breakpoint using tbreak. Confirm that it is set, and then we run the program. And having run the program, we hit the breakpoint, and now because it is a temporary breakpoint, it should be automatically removed, and we can see that this is in fact the case. Watch points break the program when a selected variable's value or a designated memory location's value changes. We can set a watch point on a variable by typing watch, followed by space, followed by the variable name. We can also set a watch point on a particular memory location. And to do this, we would type watch -L. And to do this, we would type watch -L, followed by the memory address of the location we wish to watch. However, we must dereference that location using the syntax shown, because GDB refuses to create a watch point that simply watches a never changing value. So what we are really interested in is the contents of this location, thus the need for the dereferencing. We will now look at an example of using watch points in our debugging. We will use the memory program we created in an earlier lesson, and we will try and observe the changes to the global variables called first_global_variable and second_global_variable. So we build the program, and then we run the program in GDB. We can then set a watch point for the second global variable name, and we see GDB indicating that a watch point has now been set. And then when we run the program, we can see that as soon as the value of the variable is changed, the program execution is interrupted. We're then free to examine state of the program or other aspects of the program, or we can simply step the program forward from that point if we wish, or simply continue it to its conclusion. As indicated earlier, we can also watch a specific memory location by using the appropriate dereferencing syntax shown here. And we will now take a look at an example of this. So we again run the program in the debugger and we set a watch point on the location we know is associated with the global variable of interest. We can again confirm that the watch point has been set by typing info watch points, which will list available watch points. And now when we run the program, we again break on a point where the global variable's value has changed. And we can see that the address that we set the breakpoint on is in fact the address of the second global variable. As indicated in that example, we can list watch points with the info watch points command, and we can also disable a watch point and delete a watch point by using a reference to its number in that list. So in this example, I am going to, first of all, disable the watch point I said earlier with the disable command. And then I can delete the watch point completely from the watch point list. And if we list our watch points now, we can see that all of the watch points have been removed. There are two other variations of setting watch points, and these are rwatch, which stops if the address or symbol is simply read, and awatch, which stops if the symbol is either read from or written to. So we will look at a quick example of rwatch. Again, we will set it on the second global variable. We run the program. And as soon as the variable is read, we can see that the program halts. GDB provides an option for loading programs and files through the file command from the GDB prompt, and this can be useful in many circumstances, for example, to load a core dump or a symbols file, or another binary that your program interacts with. We will now look at an example of loading a program using the file command. We have created a simple program here just to illustrate this. The main takes a number of command line arguments. We check the number of those arguments, and then we print both the arguments and the program name. So we build the program, and having obtained the binary, we then run GDB. With GDB loaded, we can then use the file command to load the actual binary itself. We now have the binary in GDB. And before running the program, we can now set arguments using the setargs command. So let's look at an example of this. We can also check these arguments using the showargs command. And we can see the three arguments that we passed in this instance. We can then run the program as we normally would, just using the run command. And we can see that the program processes the three arguments we passed. GDB can also be attached to a running process using GDB-P, and we will now look at an example of this. This can be very useful for debugging code like a service or code that is automatically started by some other process. We'll use the example of the memory program we created in an earlier lesson. We run the program. We then obtain the process ID of the program using PS. And having obtained the process ID, we can then attach to the program. We need to be sudo, of course, to do this. And as you can see, we've now attached to the program, and we can use all of the familiar commands like backtrace to examine the program or to check variables and memory locations within the program. And this is a very powerful debugging feature for running programs. Once we quit GDB, then we can see that the process continues to run. In the next two slides, we have created a GDB command cheat sheet, and this can be useful in trying to navigate the various options available within GDB. In the first section here, we have a number of commands that can be useful for setting, managing, and deleting breakpoints. Then there are commands that are useful in listing source code that you have loaded in GDB. There are a number of commands associated with navigating through GDB, and these largely control how the code is executed. And then there are specific commands associated with thread debugging. Something that is obviously very useful in GDB is displaying various variable and memory location names and contents. So there are a number of commands available specifically for that purpose. One issue that can be sometimes problematic is signal handling in programs that you are trying to debug. And GDB provides a number of commands specifically for controlling how you handle signals or whether signals are handled by the debugger. This can be useful for some programs that use automatic probing of system architecture to try and determine what type of system they're running on. Some of this automatic probing often results in illegal instruction signals, for example, and it can be useful to indicate to GDB how you would wish to handle those. We have a number of signals in the miscellaneous category, such as generating core files, displaying the program stack. Again, these can be useful in certain circumstances. And then there are a number of commands specifically associated with debugging shared libraries. Remote debugging allows developers debug code on a remote system from their local machine. And this is typically used when we are developing software for embedded systems or for remote servers. The application on the target uses GDB server to run, and we use GDB debugger on the host system, and these connect to each other over either an Ethernet or serial port connection. The dwarf specification enables debugging on an embedded target through a host PC. On the target system, GDB server uses ftrace to control the actual application execution. We're now going to take a look at a practical example of using GDB on a remote target. For this particular demonstration, I'm going to use a Raspberry Pi as the remote target, and I have built an image for the Pi using a tool called BuildRoot, which allows you to build software for various platforms, and it supports all versions of the Raspberry Pi. So having created a software image using BuildRoot, I then have access to a toolchain which allows me to cross-compile the code for the Raspberry Pi. I will start by just taking a look at the code that I have created. This is the code that will run on the Raspberry Pi itself. And as you can see, it is a very simple program. which simply prints out a message, then waits for somebody to hit a key, and then prints out a second message and exits. So I have created a simple CMake list file for the compilation of this program, and I'm using a buildroot toolchain file for the actual compilation. And the toolchain will specify the compiler to use, the location of the compiler, and the location of the root file system for the target device, which in this case is a Raspberry Pi. I can now build the code using this configuration, and I create a executable that can run on the remote system. I'll simply transfer that program now to the remote system using SFTP. In this instance, I'm using a tool called FileZilla for that purpose. So now the file has finished transfer. And now we can go to the Raspberry Pi itself. I'm using PuTTY to SSH into the Pi. We can see the program that I've copied down. And if we run the program, we can see it print its message, wait for the key press, and then exit. So now I will restart the program, but this time I will use GDB server, and I will specify an IP address and a port on which GDB server can be contacted by the host system. So the program now runs and is listening for connections on the specified port. Now returning to my host system, I can run an instance of GDB, and I use the multi-architecture version of it, GDB multi-arch. And then I specify the target. In this case, I use the IP address and the port number that I specified on the Raspberry Pi, and we successfully connect to the Pi. We can read symbols from the program. So we're now in a position to debug the code. So I'm reading the symbols from the code, and I don't have the libraries instrumented, so I can't read symbols from the libraries themselves. But you can also see on the right-hand side there that I now have successfully connected from the host, and it specifies the IP address of the host and the port number that we're connected on. I can then list the code from the host system and set a breakpoint. And in this case, I'll set it to line 22, which is the final message we print before we exit. So as you can observe, we have successfully set the breakpoint on line 22. And now I can continue. The program will continue to run, and if you again look on the right hand side on the terminal, you can see that it's now waiting for a key press. And once I press the key, we hit the breakpoint that we have set on that final message that's printed before we exit. And then I can continue again, and the program should just exit normally, or we can use something like backtrace, for example, to just look at the particular trace that led us to that breakpoint. And now we have exited, completing the demonstration. We're now going to look at an example of using GDB with VS Code. On the target side, we start the GDB server as we previously did by providing an IP address and a port and the name of the program that we wish to debug. And then on the host side, we must first install an extension which will allow us to debug in Visual Studio. My preference is the native debug extension shown here. In order to debug in VS Code, we need to create a debug configuration, and we can do this by going to Run, Add Configuration. So let's take a look now at adding a configuration for our debug. I'm showing a sample configuration file here. And let's have a look at some of the entries in that. So the type is GDB. The request is to attach to a program. We just give it a name for reference, in this case attach to GDB server. We specify the executable that we wish to debug and its path on the target board. And then we specify the IP address and the port on the target itself. And this will be the same IP address and port that we start the GDB server on. We indicate that we're doing remote debugging, and then we provide a path to the GDB multi-arch binary that we've previously used. We can then, if we wish, also set a reference to the root file system if we have libraries and other utilities which we have instrumented. So we then start the GDB server running on the target system. And then on the host system, we can start debugging. So my program is now communicating with the target, and I have hit a breakpoint I've set on the first line. And if we look at the target, we can see that we have an indication that we have connected with the host on a particular IP address. We can then single step the code if we wish, and this is a very useful feature to be able to step through the code line by line in a interactive editor. As we step through each line, we can see the corresponding output on the target shown on the left. And now we're requested to press a key to continue. And then once we press that key, we advance to the next line to print a final message before the program exits. Python code can be run directly inside the GDB process. This provides a powerful scripting environment for debugging code. Standard Python libraries can be imported, and then these can be used to further manipulate the debug environment. We can also use the Python extension to create our own custom commands, and these can be very useful for debugging complex memory structures, or, for example, probing the actual stack frame directly. Python has a GDB module which is specifically designed to aid debugging. We can import this into GDB with the following command: Python import GDB. The execute command then allows us to launch the application under Python control. The Python GDB module also allows us to set a breakpoint, as shown here, and we can enable or disable this breakpoint programmatically. This feature of the GDB module allowing us to dynamically manipulate the debug environment can be very useful. We will now look at some examples of using Python within GDB. So we're going to use a very simple program for this explanation, and we have a main function which calls a function passing an argument to it, and that function will print out that message. And then we have a second function which simply declares a local variable and then prints out another message. So we compile this code. And now we can use GDB to launch the code. We can verify that we've launched the intended code by using the list command. And we can now import the GDB Python library. And using GDB execute, we can start the program. If we hit a breakpoint, then we can either step or we can simply set a breakpoint. In this case, I'm going to set a breakpoint on line 11, which is a call to the second function. And with that breakpoint set, I now continue execution. And as you can see, I hit that breakpoint. I can use the info function to get information about local variables. And I can use the args function to get information about arguments passed to functions that I'm calling. I can move to the next command. So as you can see, using Python within GDB gives you some really powerful options for debugging. You can programmatically instrument aspects of the code. You can create and craft custom commands in Python. And this can be very useful for programs, particularly that have complex memory structures where you may need to present the information in a particular format. In the previous slides, we looked at the use of the Python extension within GDB. This Python extension allows us to create very powerful debugging tools and scripts. And these can be very useful if you find yourself debugging complex memory structures. We can define, for example, methods that print these structures, like linked lists, in a more meaningful way. We can also use Python to create tools that directly monitor register values in the processor or selected memory locations. And this feature to create custom commands in Python can be very, very useful for difficult to solve debugging problems. This slide features a number of resources that you might find useful. Debugging programs that link to shared libraries can often provide particular challenges for a developer. The shared library may not have debugging symbols by default, and we may sometimes need to load these during the execution of the program. We will now look at an example of how to do this. For the purpose of debugging the library, we have created an example that has an explicit segfault condition, and we will use this example in the course of this tutorial. We can use the ld_trace_loaded objects environment variable to trace the dynamically loaded objects, and this is equivalent to the ldd command. Let's look at an example now of this. So having now built our sample code, we can now check the shared library objects that are linked to this file. We can identify the libmylib.so, which is a library that will contain the actual fault. So we load up the program in GDB, and we can see that we have no debugging symbols enabled in this particular program. Before we execute the program, we're going to set the environment variable ld_library_path to the local directory so that it can find the local version of the library. We will then set up a breakpoint and we will execute the program. And then when we hit that breakpoint, we can display the loaded shared libraries along with their associated mappings. So let's take a look at that now in practice. We set the environment variable to point to the local directory, and this will allow the program to find the local version of the library. We now set a breakpoint in main, and now we run the program. And as expected, we hit the breakpoint that we have set. And we can now use the info shared command to look at the various shared library mappings. And we are interested, in course, in libmylib.so and its particular mapping. Now with the program at the breakpoint, we can use the add symbol file command to load a version of the shared library that contains debugging symbols. And the address we will load it at is the address we observed for the libmylib.so library mapping. We are prompted to read the symbols, and when we type Y, the symbols are read from the debug version of mylib.so. We can then simply continue running the program. So let's take a look at a practical example of this. So I'm going to add the debug version of the library. I'm going to use the address that we previously observed. I read the symbols as observed here, and then I continue running the program. And we hit a segmentation fault as we anticipated. However, now having the symbol file loaded, we can use tools like ftrace to observe the actual offending line.
Another very useful feature when debugging libraries or debugging code that are linked to libraries is the LD preload feature. LD preload is an environment variable in Linux that allows you to specify shared libraries that should be loaded before all other libraries when a program starts. Preload libraries can override or intercept calls to specific functions in other libraries or programs. And this can be very useful for adding custom behavior, debugging, or profiling without modifying the original binary code. LD preload can be used to inject debugging code into a program to trace its behavior or to troubleshoot issues. The syntax for using LD preload is shown below. So we specify the environment variable LD preload equals and then the path to the shared library, followed by the program itself. When the program then starts, it will first load this library. This can be very useful to override certain behaviors in a program.
libsegfault is a debugging library provided by glibc. It automatically dumps the backtrace and memory map when a program crashes with a segfault. The library is activated at runtime via the preload facility we looked at earlier. And this means that we are not required to do function overloading. It registers a signal handler before program execution, which prints the backtrace when a signal is delivered. libsegfault looks at segfault signals environment variable for the list of accepted signals, and by default it handles segv. The library is part of the glibc tools package, and the library can be loaded for a particular binary using the following command line. We will now take a look at an example of using this library to debug a program which has a segmentation fault in it. For this example, we've created a program called segfault, and this will deliberately create a segmentation fault when it runs. So we can build a program, and this produces the segfault binary. We then create the preload instruction by specifying the location of the libsegfault library, and this may vary depending on your Linux system. And then we also provide the binary itself. Once we launch this, then we get quite a verbose output. And looking at that output, we can see we have the various registers shown at the time of the fault. We have the instruction pointer, RIP, which is the register pointing to the instruction that caused the segmentation fault. And we also have backtrace information, which shows the sequence of function calls leading to the crash. In our case, it points to the cause segmentation fault function call and the main function in our segfault program. The memory map displays the memory regions of the process. It shows the ranges of memory that are mapped for our program and shared libraries. We can see that the segmentation fault occurred in the cause segmentation fault function within our segfault program. Continuing our examination of the backtrace from the last example, then we can use nm to get the absolute address of the function cause segmentation fault. So we simply run nm segfault, and then we can see the address of the function. And then we can take that address, which is at 1149, and we can add the offset of 18 that we found in the backtrace. So let's take a look at this now in more detail. So we run nm segfault. We then find the address associated with the function that we know is causing the issue, which is cause segmentation fault. And that's at 1149. So we copy that address, and to that address then we can add the offset that we found in the backtrace, which in our case was 80. And that gives us an address of 1161. We can now use that calculated address, and we can imply the utility address to line to find out the actual line of code that that address corresponds to. In this particular case, we are told it's segfault.c line 7, and indeed, checking the source code, we can find that that is in fact the cause of the segmentation, where we are writing to a null pointer. The kernel has the ability to save a program's snapshot in a core file when it encounters a critical error, like a segmentation fault or some other program crash. Core dumps are essential for post-mortem debugging, containing memory snapshots, variable values, call stacks, and CPU registers at the time of the crash. By default, core dumps are disabled on most Linux systems. To enable a core dump, we can set the rlimit_core to unlimited with the following command. We can also modify the naming convention for the core dump by writing to procsys kernel core pattern. We will look at an example of both of these commands now. Once we enable core dumps, we can simply run our executable program, and if a program crash occurs, we should be left with a core dump in the directory in which the program ran. We can then use gdb to examine the core file. The command for that would be gdb, the name of the binary, -c, and then the location of the core file. If the program was compiled with debug information, that information will be available once we load up the core dump. We can then use facilities like backtrace, as shown here, to try and determine the program execution up to the point of failure. We can also use many of the other built-in GDB commands to get information about the memory and the registers at the time of the crash. This ability to use core dump files is a powerful debugging feature because it means we can collect a core dump on a target system that may have limited debugging tools installed on it, and then examine that core dump file on a separate machine that has all of the necessary tools.
This slide summarizes some of the references that we used when researching this particular section of the course.
We will also now take the opportunity to review some of the very important topics we covered in this section. In this module, we reviewed application debugging techniques and the tools that can assist us in that process. We explored several tools collectively known as bin utils, including readelf, object dump, object copy, nm, and address to line. These tools provide essential insights into binary files. Additionally, we examined tools that give us insight into shared libraries to better understand their structure and usage. We also delved into the powerful capabilities of the GNU Debugger GDB, an indispensable tool for Linux software engineers, and we discussed how optimization affects debugging processes and explored techniques to work effectively in an optimized environment. We also highlighted how GDB's functionality can be extended using Python, enabling advanced debugging features. Practical examples demonstrated including debugging shared memory, diagnosing segmentation faults, analyzing crash reports, interpreting core dumps, and performing backtrace analysis. These examples illustrated the practical value of debugging tools in a real-world scenario.
In this module of the course, we will explore the importance of memory management in application development. We will cover some common issues related to the memory management, such as segmentation fault, memory leaks, buffer overflow, etc. We will also cover the available tools and techniques to debug these memory issues. Tools like static code analyzer, Valgrind, sanitizer suits, libefence are helpful to uncover memory issues in the application code. Memory management is crucial in programming as it ensures efficient use of system resources, stability, and performance. Application programming, which mostly involves allocation and deallocation of memory resources. In languages like C and C++, which are unmanaged in nature, memory mismanagement can lead to unstable program and even compromise system security. Proper memory management ensures optimal utilization and helps prevent common memory issues. Memory issues lurking in the application code can impact the application or system in many different ways, such as you could see a performance degradation, which can slow down the application and leading to a sluggish user experience. Or we could have a memory related error like segmentation fault, which can cause the application to crash and which could potentially make the system unstable. More importantly, we could have security vulnerabilities such as buffer overflow, which can be exploited by an attacker to compromise the system security. Recently, to address these concerns, CISA, which is a US government agency, recommended that developers should transition to more memory-safe programming languages such as Rust in C in place of C or C++ to address the growing concern around memory-safe programming. Refer to this link, which points you towards the notification released by the CISA. In the preceding slides, we discussed about the importance of memory-safe programming. In this section, we talk in detail about the common memory issues, starting with the segmentation fault. A segmentation fault can happen when a program tries to access a non-existing virtual memory segment, or in simple terms, a virtual memory page which does not exist. Or the segmentation fault can happen if the program tries to access an existing virtual memory segment in a different way as defined by its attributes. For example, the program tries to execute the data in a non-executable segment, or it writes the data into a read-only segment. So as a consequence, kernel will deliver a segue signal to the offending process, and it usually results in the termination of the process. Now let's look at an example to understand the seg fault in more details. We are referring to the segfault example which was referred in our course material. The C code shown here has an explicit segfault condition. The main function is calling the cause segmentation fault function. In the cause segmentation fault function, we are declaring an integer pointer which is referring to a null, which means it is not pointing to any existing virtual memory segment. Further in the code, we are trying to dereference this integer pointer, which essentially means we are trying to refer to a non-existing virtual memory segment, which is one of the condition in which kernel will deliver the segue signal to our program and cause to crash. Let's try to build and run this example. So we are using a helper build script to build this program, and our application binary is generated with the name called segfault. When I run this segfault binary, it will cause the program to crash and dump the code depending on your codem settings. The codem file can further analyze for debugging the exact root cause of this crash. The next common memory related issue we face is memory leak. It is a condition that occurs when a program fails to release the memory that is no longer needed. Memory leak gradually consumes available memory resources over time, potentially causing the performance degradation, and during the longer run of the program, it could eventually cause the program to crash. Common cause of memory leak include not deallocating the dynamically allocated memory, losing the references to the memory block, and failing to release the resources properly. In the given code section below, we are trying to demonstrate a memory leak scenario. We are dynamically allocating memory for an integer array of 5, and then we are initializing this integer array. While exiting the program, we are not calling free to deallocate the dynamically allocated memory. Now this will lead to the memory leak in the system. Buffer overflow is another type of software vulnerability that occurs when a program writes more data to a buffer than it can hold, which causes the excess data to overflow into the adjacent memory location. Depending on the location of buffer in memory, the buffer overflow can be categorized into stack-based and heap-based. It can lead to memory corruption, program crashes, or unauthorized access to a system, making it a significant security risk. Referring to this code section here, which demonstrates the buffer overflow condition, the program declares a buffer of size 5 integers. Further, we are writing into a location which is outside the bound of the array. This will produce the unexpected behavior in the code. So far, we discussed about the various type of memory related issues. Detecting and resolving these issues is crucial for application development and system stability. There are various tools available to identify and report the memory related issues. In this section, we will explore these tools and techniques. Static code analyzer is the first level of defense available to us. It is a software analysis tool that examines the source code for potential issues without executing the code. It performs a comprehensive code examination, including the analysis of code patterns, control flow, data flow, and to identify the potential issues, including memory related problems and the vulnerabilities. Static analyzer helps catch the memory issues early in the development process, which reduces the likelihood of costly and disruptive issues later on. The next tool in our list is Valgrind. Valgrind is in fact an instrumentation framework for building the dynamic analysis tool. It includes a suite of tools for memory debugging, memory leak detection, and profiling. For example, memcheck is a memory error detector and is a default tool in Valgrind. Similarly, cachegrind is a cache profiler, callgrind is a call graph profiler, hellgrind is a thread error detector, and massif is a heap profiler. So in this section, we will discuss the memcheck tool and cover the other tools into the later section of the course. Valgrind operates by running the program in a virtual machine that monitor and analyze the memory and CPU usage of the program. Because of this instrumentation added by Valgrind, the execution speed is significantly slowed down, which makes the program only suitable for the debugging but not suitable for the production environment. As discussed in the last slide, memcheck is the most widely used and the default tool in Valgrind. Memcheck works by intercepting the memory operation related calls such as malloc, new, free, delete. It tracks all the read and write operation and help us to identify various memory related issues such as memory leak by identifying the memory block that were allocated but not freed, or uninitialized memory use by detecting the use of uninitialized values, invalid memory access by finding out of bound array access or invalid pointer dereferencing, bat free of heap blocks, which means double freeze and mismatch freeze, overlapping source and destination pointers in memcopy and related functions. So we can figure out all these issues using Valgrind as a tool. The usage of Valgrind tool is given here. So if you want to run the program under a Valgrind, you could call Valgrind command line option with hyphen hyphen tool equal to memcheck, which is the default tool for Valgrind, hyphen hyphen leak check equals to full, and your program binary name. You could also set leak check to summary. That way the Valgrind will only report how many leaks were occurred. If the leak check is set to full or yes, each individual leak will be shown in detail and counted as an error. Let's understand how Valgrind is helpful to find memory related issues in the application program. We are using a program called Memory Leak, which is available with this course material. In this example, we are dynamically allocating memory for an array with 5 elements, but not freeing it later when the program is finishing. We will now compile the code and execute it using Valgrind to understand how Valgrind report this memory issues. So for compiling, I'm using our helper build script. I have a binary called memleak. I'll run this binary using Valgrind. My command line options is hyphen hyphen tool memcheck hyphen hyphen leak check equals to full and the binary name. So here's the report which Valgrind generated. As you can see in this Valgrind report, in the section called heap summary, it reports 20 bytes of memory was allocated by malloc call at line number 5. The allocated memory was not explicitly freed, so Valgrind reported this memory block as a lost, or in other words, it is a memory leak. In the preceding slides, we discussed about Valgrind in general. Now in this slide, we will discuss about GDB support available in Valgrind. Because Valgrind uses a synthetic CPU, not the host CPU, directly debugging the program running with Valgrind is not possible. For this reason, Valgrind provides GDB server support, using which GDB can interact and control the program flow. This can be achieved by running Valgrind with vgdb command line option as shown in this slide. Once we run the program with Valgrind GDB server, it will then instruct to run the same program with GDB in another shell and wait for the GDB connection. From another shell, use GDB command with program name and connect the GDB with Valgrind GDB server using this command. Once we have the connection, we can then debug and control the program using normal GDB options such as inserting a breakpoint, continue, etc. Let's understand this using an example. In this demonstration, we are going to run memleak program in Valgrind with VGDB support turned on. As you can see on the screen, we are using memcheck tool along with the full leak check. To turn on the VGDB support, I'm using VGDB command line option along with VGDB error. After executing this command line, Valgrind is asking to run the same program with GDB in another shell. It is essentially waiting for GDB to connect with the GDB server and control the program flow. Now we go into the another terminal and type GDB with our application binary name, which is memleak. And to connect GDB to VGDB server, I will type in target remote pipe VGDB. So we have a connection now with the Valgrind VGDB server, and we can now continue to debug the program. For example, I can add a breakpoint on main and step through the code until it finished and see the activity in the GDB server. So we have a breakpoint on main. We will continue to run this program. The program hits the breakpoint. I'll use N to step into the next instruction, which is a print instruction. Ideally, this print should be visible in the GDB server. We can have a look into the GDB server. We have a print here. We go back, and now we will continue this program until it finishes. After finishing this program, we will see a memleak report in the Valgrind, similar to what we see in our earlier demonstration. So in the GDB server, now we can have a memory report, which basically pointing out to the memory leaks, similar to what we saw earlier. 20 bytes of memory leaked and it was allocated in the main line number 5. So this is how we can use Valgrind GDB support to connect to GDB and debug the program flow. In the preceding section, we discussed about Valgrind, which is a dynamic binary instrumentation tool and works in a virtualized environment. In this section, we will turn our attention to another set of tool called Sanitizer. A sanitizer is a runtime analysis tool which instruments the code at compile time for runtime analysis. It can detect problems like memory error, undefined behavior, race conditions, and similar bugs. In general, Sanitizer relies on compiler instrumentation, which means compiler modify the code to insert additional checks around the memory access and reports the issues when it finds the memory violations. Sanitizer also use various other techniques like shadow memory, which is used to store metadata about memory status, whether it is valid, invalid, or freed. There are range of sanitizer available, namely address sanitizer, uh, thread sanitizer, undefined behavior sanitizer, and more. And these sanitizer are available for both user space and the kernel space. Major compilers such as GCC, CLang provide the support for various sanitizer. Please refer to the given links here to check the available sanitizer options for a particular compiler. Now we will discuss each of the sanitizer in more detail. The first sanitizer in our list is address sanitizer, also called ASAN. Address sanitizer is a runtime memory error detector for C and C++. ASAN follow the principle of compiler instrumentation and shadow memory to detect and report the memory issues. ASAN helps identifying memory-related issues such as use after free, heap buffer overflow, stack buffer overflow, global buffer overflow, use after return, use after scope, initialization order bugs, and memory leaks. To enable ASAN, use fsanitize address compiler option while compiling the code. It is also recommended to use fno omit frame pointer compiler option to get a reliable stack trace when an issue is detected. Upon detecting a memory issue during the runtime, ASAN will print a error message and a stack trace indicating where the issue is occurred. In this example, we are running a program with an explicit memory leak and it is compiled with the address sanitizer. ASAN detects and reports the memory leak in its report. We will discuss this report in our demonstration. The added instrumentation significantly slows down the program and it is recommended to use the ASAN in development and testing environment only. We will now demonstrate the use of address sanitizer. Before we look into the code, it is important to note that you need a libasan library installed on your system. In Ubuntu system, it can be installed using sudo apt-get installed libasan8. Also note that number convention in libasan, the number is used to match the compatibility with the version of libasan and the GCC version you are using. For example, in this case, libasan 8 is compatible with GCC version 12. We can confirm this by using a command called apt-cache show package name. So our package name is libasan8 and we can go into the dependencies section, see the GCC version used here, so GCC 12, and my GCC version is 12. We can check that using GCC --version command, GCC version 12. So you need to install a compatible version of libasan into your system, which basically compatible with your GCC version. Now, the C code we are using to demonstrate ASAN has three explicit memory issues. Let's look into those issues. The first issue is out of bound issue. In this case, we have an integer array of 5, and while initializing this array, we are trying to write into the sixth location of the array, which will cause the out of bound array issue. The next condition is use after free. We are initializing a dynamically allocated memory of size int and allocating it to a pointer called ptr. And then we are initializing this pointer with the value and then later freeing this pointer. To override that memory block, we are reallocating some memory and initializing it with some value. And then in the next line in the printf statement, we are trying to dereference the same pointer which was freed earlier. Now this is a condition where we are trying to use a pointer which was freed earlier and it will cause a use after free memory issue. So the next issue we have memory leak. In this case, we are trying to allocate memory for 10 integers and initializing it. And while the program is finishing, we are not calling the free call explicitly. Please pay attention to these macros. These macros are defined to cause the memory issues. If you want to fix any of the memory issues, you can comment out the corresponding macro in the top of the file. In the CMake file, we are using fsanitize address compiler option to invoke address sanitizer along with the fno omit frame pointer to have a reliable stack trace. We will now build this program using our helper script. Our application binary is called asun demo. Using LDD, we can confirm or we can validate that libasan is linked to the application binary. Please note, by default, upon encountering an error, libasan will abort the program. This behavior can be changed by using halt on error asan option. You can refer to the various asan option on the link given on our slides. Now we will execute our program, and the first hit we got is out of bound error. Let's look into the key details from this report. In the heading itself, we have the issue name along with the address where the issue occurred, the program counter, and various other CPU registers. It tells the issue happened when the program was trying to write of the given size at this particular address. This block shows us the stack trace, and the zeroth frame will tell exactly in the code where we had this out of bound access happened. Further, we have associated object which cause the buffer overflow condition. In this case, it is an array with name ARR, and the array is allocated at offset of 32 to 52. The excess occurred at offset 52, which overflow the last byte of the array. Next, we have shadow memory mapping. Shadow byte represents the metadata about the application memory. Each shadow byte corresponds to 8 bytes of application memory. The pointer points to the shadow memory mapping related to the buggy address. The addressable memory of the array is guarded by inaccessible memory zones. As you can see, F1 represents the left stack left guard zone and F3 represents the right guard zone. Zeros represent the addressable memory, and the number like 04 here represent the partial addressable range. 04 means 4 out of 8 bytes are valid. So any memory access out of the addressable region will cause the sanitizer to capture that and report as an issue. Now let's fix this out of bound issue and try to find another issue which is present in our code. We are now commenting out the cause out of bound issue. Now this will ensure that we are writing into the proper locations of the array. We'll build the code again and run it. Now the next issue we are hitting with is use after free error. Looking into the report, the issue caused due to use after free error while reading the memory size of 4 at this given address. Again, this block represents the stack trace, and the 0th frame will tell you exactly where this use after free issue happened in the code. The next line here represents the attribute of the object which causes the issue. The allocated memory block was 4 byte in size, starting at this given address and ending at this address. The problematic access occurred exactly at the start address of this region, and the 0 byte indicates that the memory region was freed earlier. These two traces indicate the history of the object. The first trace tells about where it was freed, and the next trace tells about where it was allocated initially. Moving to the shadow memory section, we will now analyze the pointed buggy address. The FA represents the heap red zone, which is a guard region used to detect the buffer overflow, whereas the FD represents the freed heap region, indicating that memory was previously allocated but it's now freed. So shadow memory pointing to the exact location where it is freed but referred by the program again, and that causes us the use after free issue. Now let's fix this use after free issue and see what all remaining issues exist in our program. We'll now go back into our code, fix the use after free issues, rebuild our code. Let's rerun our program. SN is reporting the memory leak issue it detected in the code. The stack trace is pointing towards the location of the leaked memory, and it is pointing towards the line number 37 of main.c. The summary is pointing towards the number of bytes leaked along with the number of allocation. Let's fix this memory issue in our code and see what all pending issues Asan reports. So now no more pending issues and the program will execute normally. I hope this demonstration was helpful for you to understand the address sanitizer and its usage. The next sanitizer we will discuss is memory sanitizer, or MSAN. MSAN is a runtime uninitialized memory read detector, which means whenever a program tries to read an uninitialized memory, MSAN detects and reports the same. MSAN uses compiler instrumentation and shadow memory. It tracks memory initialization using shadow memory, where each byte is mapped to indicate whether the memory is initialized or uninitialized. MSAN helps us to detect the following cases. If uninitialized value was used in a conditional branch, or if uninitialized pointer was used for any kind of memory access, or if uninitialized value was passed or returned from a function call, or if uninitialized data was passed into some library or libc call. The support for MSAN is only available in the CLang compiler. If you want to use MSAN, to enable it, you could use fsanitize memory compiler option along with fsanitize memory track origin and fno-omit frame pointer. Thread sanitizer, or TSAN, is a tool that detects data races in C and C++ program which uses pthread library. A data race is a condition which occurs when two threads access the same variable concurrently and at least one of the access is the write. As shown in the example here, we could use fsanitize thread compiler option to enable the compiler instrumentation for TSAN. Upon finding a data race condition, TSAN will print the error report on the console. We are now going to demonstrate thread sanitizer using an example. Setup-wise, we need libtsan library installed on the system, and in Ubuntu system it can be installed using sudo apt-get install libtsan2. Libtsan2 package is compatible to GCC version 12. The example we are using in this demonstration consists of an integer named shared resource, and it is being accessed by two threads simultaneously, which results in a race condition. In the CMake file, we are using fsanitize thread compiler option to invoke the TSAN along with fno omit frame pointer to have a reliable stack trace. We will now build this program using our helper script. Our application binary is TSAN demo. We will first confirm using LDD that libtsan is linked with our application binary. In the current version of TSAN, I'm facing a fatal error after executing my program binary. Upon researching, the resolution for this issue is to disable the address space layout randomization in the kernel. We could do so by echoing 0 into a file called proc.sys_kernel randomized VA space. Now we'll run our program as normal. As expected, tsyn detects and report the concurrency issue. Let's understand the error report and the key details into it. The issue we faced is data race on the given PID. Now it is pointing out that two threads are simultaneously accessing the shared resource. One with the read access and another thread is accessing with the write access. The shared resource resides at line number 7 in the main.c file. Next line provides us the attribute of the shared resources, and in this case, it is a global type int and which resides at this given address. And finally, in the summary, we have the same conclusion which we discussed above, that the issue happened due to the data race condition and the location for the issue resides in main.c line number 7. The function name is increment resource. Now we will discuss undefined behavior sanitizer, also called UBSAN. UBSAN is a runtime error detection tool that identifies undefined behavior such as signed integer overflow, invalid shift operation, dereferencing, misaligned or null pointer, type mismatch or invalid cast between different types. For the exhaustive list of undefined behavior, you can refer to this document. As per your need, you can select appropriate check available in this list to use in your program debugging. For example, if you're interested in the misaligned pointer detection, you could use fsanitize alignment. Or if you're only interested to find out the integer divide by 0 condition, you could use fsanitize integer divide by 0 compile time option. Similarly, you could also use groups which represents multiple checks at once. So for example, fsanitize undefined basically represent majority of the checks defined in the above list. UBSAN solely relies on the compile time instrumentation checks to detect different undefined behavior at runtime. To start with, you could use fsanitize undefined compiler option to enable most of the undefined behavior checking. Upon detecting a issue, UBSAN logs a detailed message with the type of undefined behavior, source code location, and a backtrace. Let's take a look at UBSAN demonstration using an example. Setup wise, as with other sanitizers we discussed earlier, we need a libubsan library installed in the system. And in Ubuntu system, it can be installed using sudo apt-get installed ubsan 1, whereas ubsan 1 package is compatible to GCC version 12, which we have in our system. Code wise, we are trying to track two explicit conditions. The first one is divide by 0, wherein we are trying to divide x, the value is 10, with y, which has the value 0. And another condition is integer overflow, wherein we define x with the max integer value, and in the print statement we are incrementing the x with 1, causing it to overflow. While debugging, you could fix these issues by commenting out these macros depending on the issue you want to fix. In the CMake file, we are using fsanitize undefined compiler option to invoke the ubsan sanitizer along with fno omit frame pointer. Now we'll build this code. using our helper build script, and we have ubisan demo application. Using LDD, we will confirm that libubisan library is attached to our program. When we run the code, ubisan reports the first encounter of divide by zero case, and it also reports the location of the issue. In this case, it is line number 9 on main.c file. Now let's fix this code. Let's fix this divide by zero condition and re-execute the program. The next issue we stumble upon is signed integer overflow. Ubisan reports the location of this issue, and in this case it is line number 16 in main.c file, along with the associated violation. libefence is another option to detect some of the memory issues. libefence is a lightweight library that helps to catch some common issues like buffer overflow and use after free memory errors. Implementation wise, libefence allocates extra memory pages around the dynamic memory block and marks them as unreadable. So if the program tries to access memory beyond its allocated bound, it will lead to accessing the memory segment which is marked unreadable by libefence, and this will result into a segmentation fault due to the fact that program is trying to read an unreadable page, or in other words, it is trying to access an existing virtual memory segment in a different way as defined by its attribute, which was one of the condition of having a seg fault. Further, we could either statically link the library in the program or preload it using LD preload environment variable. So we are showing an example here. We will also discuss about this example in our further demonstration. If you want to install libsystem in a Ubuntu Linux system, you could use sudo apt get install electric efence package, and also it generates core dump. So it is recommended to have the core dump enabled in your system so that once you have the seg fault, you can at least try to understand the root cause of the seg fault by analyzing the core dump into GDB and pinpointing the exact location of the error. So let's understand how to use libefence using an example. We will now look into an example to demonstrate libefence along with the associated setup. We need libefence library installed on the system, and on Ubuntu you can install it using sudo apt-get installed electric efence. We also need to have a working core dump mechanism in the system. By default, in Ubuntu system, the core dump is managed by a service called app-port, which is a system error reporting service. We can confirm this behavior by reading into this file called cat proxys kernel core pattern, and it is referring to the app port service. If you want to manually control over the core dump, you would need to stop and disable the app port service with the systemctl command. System. Okay, upon disabling the app port service, it will ensure that it does not handle the core dump service automatically. We can confirm this by looking into the file pattern inside the same file, proxys kernel core pattern, and now it is referring to core. This means the core dump will be generated in the current directory itself. Next, we will use ulimit command to set the core file size to unlimited. Let's now look into the code we are using to demonstrate the libefence. So this code has two memory violations. One is the out of bound array access and another one is the use after free. In terms of out of bound access, I would like to mention an important point on how libefence detects an out of bound access. To catch the overflows, electric fence uses guard pages around the allocated memory and mark it as inaccessible. As a result, electric e-fence tries to align the end of the allocated block with the start of the guard page by padding that memory block. It may not detect the out of bound access within the same page as there is no page boundary violation occurs. For more detail, refer to the word alignment and overrun detection on the libefence man page. In the out of bound demonstration, we are dynamically allocating a buffer little short of a page size. We are then trying to write into the buffer, and the first case is writing within the array bound, and the next case is technically an overflow, but it is falling into the padded region into the same page, so it will go undetected using libefence. And the third write, we are writing into the guard page, which will cause the segfault and the program to crash. The next condition is use after free condition. Electric e-fence detects the use after free error by placing allocated memory in the protected region aligned with the guard pages. When the memory is freed, it marks the corresponding page as inaccessible using the memory protection mechanism like mprotect. Any subsequent attempt to read or write the freed memory triggers a segmentation fault. In this block, we are trying to access an integer pointer called PTR, which was freed earlier in the program, and this will cause the program to segfault. Please note, while using or while debugging, you could fix these issues by disabling or commenting out the corresponding macros here. Let's now try to execute the program using libefence. We will now build this program. I'm using my helper build script. The libefence binary or the application binary is libefence demo. We can execute this program using ld preload environment variable, wherein I'm trying to preload this libefence shared library before executing the program. You could also statically link this library into your code. So as you can see, I am hitting with the segmentation fault and I have a core dump already generated here. I could use GDB to inspect the core dump with command called GDB and using my application binary along with -c and the core dump file name. The core dump is pointing out that my program received a segv segmentation fault while it was trying to write onto this page size, array with the page size offset, which is basically overflowing into the guard page as we explained earlier. Now let's fix this out of bound issue and try to run the libefence and see if we have any other issue in our code. So I'll rebuild my program using my helper script, and I will rerun using ld preload environment variable. And the program did segfaulted again, and this time my core file is this one 23089. So I'll use GDB again to inspect the core file. All right. In this situation, GDB is pointing out that the program was segment fault and received the 6segv signal while it was trying to access the integer pointer given at this address. or in this print statement. I hope this demonstration is helpful for you to better understand the libefins. So far we covered the types of memory related issues and various tools available to catch these issues. It is recommended to adopt the best practice for memory management to reduce the chances of introducing memory related issues in the code. Practices like allocating memory dynamically when needed, so only allocate memory whenever it is necessary, otherwise use stack memory for small and short-lived variable. Deallocate memory properly. Always ensure that you're releasing the memory which you allocated dynamically when you're done with it. This will prevent the memory leak. Avoid manual memory management. Use higher level abstractions and smart pointer in case of C++ whenever possible to manage memory automatically. This reduces the risk of memory leak and other errors. Check for null pointer. Before dereferencing a pointer, ensure it is not null to avoid the crashes. Bound checking. So whenever we are working with array, use library functions or language features to check the bounds. For example, in C++, we could use vectors or use the string n copy of the string functions. Avoid memory leaks. Regularly inspect and analyze your code for memory leaks using tools like Valgrind and Address Sanitizer. Understand ownership. Clearly define the ownership of objects and memory. Understand who is responsible for allocating and deallocating the memory and follow that ownership pattern consistently. Defensive programming. Practice defensing programming by validating input parameters, checking return values from the memory allocation function, and handling the error gracefully. Code reviews. Conduct your code reviews to catch memory management issues early in your development cycle, as these can be challenging to debug once these issues occurs. Move to memory safe programming. Most importantly, you could prioritize moving to the memory safe programming languages like Rust over C and C++ for all the future development. I have provided some reference links for some of the topics that we discussed in this module. To sum up, we discuss about the common memory issues such as segfault, buffer overflow, use after free, etc., along with the available tools to detect these memory issues. Tools like Static Code Analyzer can help detect issues early in our development cycle. The more powerful tools like Valgrind, Sanitizer, those are helpful to catch not so obvious issues, but these are only suitable in the debugging environment. I hope this module will help you to understand and debug these memory issues in your project. Do refer to the example code provided with the course material and try it your own. This marks the end of part 1 of Linux debugging course. To summarize, we begin with an overview of Linux OS architecture, discussing the memory addressing in Linux along with its core building block. In the module 2 of this course, we explored basic Linux analysis and observability tools, helpful in understanding system state and behavior. Module 3 delved into dissecting application binaries using tools like binutils and debugging with GDB along with application core dump analysis. Module 4 focused on addressing common memory issues in user space application and leveraging tools like Valgrind, Sanitizer to detect and resolve these problems. In the part 2 of the course, we will dive deeper into advanced debugging techniques and discuss topics like tracing, profiling, and kernel debugging. Stay tuned for the more information on the part 2 of the Linux debugging course.